Okay, so we started after the second midterm exam discussing magnetic force. So if you have charge, moving charge exposed to the magnetic field, and it's very important, charge must move. As I told you, everything in the world of magnetism is in dynamics, right? So charge must move, must be in dynamic in order to experience magnetic force, right? And it's one of the fundamental equations, so it's written based on observation. So nothing to discuss, just we need to remember this. So force equals Q V cross B. Right, and so magnitude, it's a QVB times sine of angle between them. Direction, right hand rule number 2, and it's not over. You need to sort of make like 1.5 steps. First, you need to find direction of the cross product, V cross B, right hand rule number 1. And then after finding the direction, quickly look at the sign of the charge. If charge is positive, then direction which you just found is the correct direction for the force. If a charge is negative, then you need to flip that direction which you just found. Then if you have a bunch of charges drifting in the same direction, which is effectively a current, right? And again, if you expose it to the magnetic field, of course, there must be magnetic force acting on the wire with the current. Let's assume that a wire of length L is exposed to the magnetic field. And for simplicity, let's assume that the magnetic field is uniform. That's what we usually had in our problems, in our situations. So in this case, force acting on the wire of length L can be found by using this I L cross B, right? So in this case, finding the direction is easier, only one step. You just need to find the direction of the cross product L cross B, right? Because current, absolute value of the current, it cannot be negative, right? Then, one subtle moment. L is presented as a vector. So magnitude of L, it's just the length of the wire. Direction of L is determined by the direction of current. Here we have only one direction connected with the wire, direction of the current. So that's what determines direction of L. Okay, so that's what we used. And after that, we dived into the Faraday's law. All right. Very interesting phenomena. All right. So if you have, actually, where's my loop? Here. Right. I just realized that I need some props. Right. So if you have some conducting loop exposed to the magnetic field, of course, you can calculate magnetic flux. If that magnetic flux changes in time, as a result, there will be induced current produced in the loop. Clockwise direction or counterclockwise direction, that's the second story. But first, EMF is produced and current is produced. And of course, it's another fundamental law, right, which is written based on observations, tells us EMF, total EMF in the loop, can be found by calculating the negative rate of change of the magnetic flux, minus d phi over dt. And magnetic flux, B dot A, right, where A is the area vector, right? And area vector, for this loop, it's up to you. You can position area vector in this direction, align it along that direction, or in the opposite direction. It's up to you. In this case, you have freedom, right, to choose the direction of the area vector. But it must be perpendicular to the area, perpendicular to the loop, perpendicular to the loop. Then, okay, so minus give us a direction of EMF and direction of the current. Dealing with that minus, it's not the most pleasant experience. So as a result, if something not pleasant, of course, researchers try to find a way of avoiding it. And so Lenz came up with the rule, which happens to be very useful, right? So Lenz introduced this rule. So if you have a loop, if magnetic flux through this loop increases, magnetic flux produced by the external magnetic field increases, then a loop doesn't like it. You remember, a loop wants to keep magnetic flux as constant as possible, according to this rule, right? So if flux increases, the loop rebels. It behaves like Che Guevara, and it starts driving an induced current in such a direction so that within the loop, an induced magnetic field will be in the opposite direction to the direction of the external magnetic field. We've practiced this rule, right? Okay, and it's a first situation when magnetic flux is increasing. But if a magnetic flux produced by the external magnetic field is dying, again, loop doesn't like it because it wants to keep flux as constant as possible. If flux is dying, then the loop becomes supportive, behaves like Florence Nightingale, right? It will start driving an induced current in such a direction so that the induced magnetic field, direction of the induced magnetic field, is the same as the direction of the external magnetic field, right? Okay, we will practice that. So once we were done with Faraday's law, we moved and started discussing inductance. And it makes sense because Faraday's law lies behind behind the work of inductors, right? So if you want to explain how solenoid, which is typical inductor, how inductors work, if you want to explain that, you need to use Faraday's law, right? Faraday's law behind all of this. So first, we introduced an inductance in this way. So you calculate the total flux through that inductor and divided by the current. So that's how we introduced inductance by definition. Right? Okay, then this formula can be applied to find inductance of any object. Solenoid, a loop, wire, any object you can apply it, right, in order to calculate inductance. But if you apply it to find inductance of a solenoid, which is, I told you, typical inductor, we found that inductance of the solenoid, it's a mu naught, n squared number of loops, a cross-sectional area of the inductor, and divided by the total length of the solenoid. All right, then, next question. What if you have a solenoid and you want to find the potential difference across the solenoid? Potential difference between which points? Final point and initial point. How can we find out which point is final and which point is initial? Original current enters into the solenoid at this point. That's initial point. Current leaves the solenoid at that point. That's the final point. So delta V, it's a V final minus V initial. That's how. That's what delta V is in this case, right? And we just applied Faraday's law. Just a half a line derivation. I wouldn't even call it derivation. But anyway, delta V is equal minus inductance times rate of change of the magnetic flux. Rate of change of the electric current. Sorry, rate of change of the electric current. So minus L di over dt. And you need to understand, this delta V is produced by this solenoid, right? You know, I told you it's the product, I know, labeled made in China, made in, I know, Philippines, made in whatever, right? So this can be stapled. Made in solenoid, produced by the solenoid, because you remember what's the one of the major role, one of the roles of an inductor in the circuit. It allows us to store energy in the form of the magnetic field. Okay, so it has some amount of energy, and that energy can be used to produce this potential difference and drive an additional current in a proper direction. We will look at the examples. Right. Okay, so after discussing inductance, we sort of finalized, we wrote down all Maxwell's equations. I didn't write them over here, right? And after that, we moved into optics, because electromagnetic wave is one of the phenomena which can be explained by Maxwell's equations. So if you massage Maxwell's equations, you will end up with electromagnetic wave. And so naturally you move into optics from the electromagnetic theory, right? Okay, and of course, before we moved into optics, of course, we discussed traveling wave equation, because it's everywhere in optics, right? So we introduced the traveling wave, and this is the equation of the traveling wave, which describes any wave. It doesn't matter if that wave transverse or longitudinal. So why? Okay, what is y? Again, I will probably use the chord, which is still here, right? So if we use the wave on a chord, so y, it's a displacement of a particle of the medium. Okay, this is the medium, the chord, right? Displacement from the equilibrium. So this is the equilibrium position. Y, it's a displacement. What is x? It's a direction along which wave propagates. So let's assume that this is the x, my positive x direction. Right. Okay, this is the case of a transverse wave. Okay, so then equals to the amplitude, sine, periodic function, of course, must be, and it depends on two variables, x and t. So equals to kx plus minus omega t and plus initial phase. K, it's a wave number, basically spatial frequency. X, spatial variable. So pretty much all spatial information about the wave can be found in this term. Then omega, angular frequency, meaning just temporal frequency, right? Then t, of course, temporal variable. Again, it means that all temporal information about the wave is in this second term, omega t. Phi naught, just initial phase, which is basically shifts the wave along, in this case, x direction, right? For initial phase can be positive and negative. As a result, wave can be moved forward or back, right? Then, plus minus. Plus between these two terms means that wave propagates in the negative x direction. Minus indicates that this wave propagates in the positive x direction. So you see that reverse. Minus means in the positive x direction, plus means wave propagates in the negative x direction. Then speed of the wave, like every time speed, in order to find speed, you need to mix spatial quantities and temporal quantities, right? Like in physics 1, in order to find the speed of an object, you need to take the distance and divide it by the time. Spatial quantity and divided by the time, which is temporal quantity. Okay, temporal variable. In this case, speed of the wave can be found in two ways. Either you take omega, which is the temporal quantity, and divide it by the k, which is spatial quantity. And it can be also found by, okay, from here you can easily move to there. So wavelengths times frequency, right? Speed can be found. And I told you that speed works effectively like a bridge between temporal quantities and spatial quantities. If there are tons of information about behavior of the wave in space, but you need to get some information, some time information, speed helps to move to the world of temporal quantities and find whatever you wanted to find over there. Sorry. Then, after that, once we were ready, we moved into electromagnetic waves. Right? In the electromagnetic wave, we have two traveling waves moving together, right, in unison, in like a happy couple. You remember I told you about the perfect couple, right? True love, right? All right. So in this case, let's assume that electric field, which forms a traveling wave, oscillates in the y direction. You see, we have coordinate system x, y, and z. And the electric field oscillates in the vertical direction, which is the y direction. And electric field forms electromagnetic wave. Forms traveling wave. And that traveling wave is described by the traveling wave which we just introduced. Right? And what is important? A few pieces. First of all these three directions of the electric field, magnetic field, and direction of propagation, they're perpendicular to each other. They must be perpendicular all the time. God created nature this way, right? We're just modeling and describing it. Then, amplitudes of the electric field and magnetic field are deeply connected. Through the speed of light, it basically means if you have information about electric field amplitude, you can tell immediately that basically you know magnetic field amplitude, right? So all the time electric field is way stronger than magnetic field strength because of the speed of light. Equations. Traveling wave equation describing electric field. Look, this subscript E sub y. This subscript tells us along which direction electric field oscillates. In this case, along y direction. But the wave propagates in the x direction. That's probably the point where most of the mistakes students make on the final exam if I give a problem about electromagnetic wave. It's a mess about directions. This is a transverse wave. Electric field in this case oscillates in the y direction, but it propagates along x direction. And then magnetic field, subscript z, tells us that magnetic field oscillates in the z direction, but the wave propagates along x direction. So lots of mistakes, maybe like, I don't know, up to 40% in this place, okay, these directions, y, x, and z. It's not that complicated. You just usually it's either given in the statement of the problem along which direction y, or I mean E or B oscillates, right? Or maybe on the diagram there is a picture, and it on the diagram you can see along which axis fields oscillates and along which direction they propagate. So you just need to move and write these traveling wave equations properly, right? So directions of oscillations, y, z, and direction of propagation of the wave, Okay, so done. And again, another thing which, again, lots of students made mistakes. Let's say in the problem I give information about the electric field. Maybe even the equation of the electric field is given. And then I ask, okay, write down the equation for the magnetic field. And lots of math. Although, look, this part, sine kx minus omega t plus phi naught, exactly the same here for the electric field and for the magnetic field. What you have to do, just need to rewrite it. What's the difference between these two equations? Only amplitude, but you remember amplitudes are connected to the speed of light. So if you know E naught, you can find B naught easily. But I see in the exam quite often, students just grab the amplitude of the electric field and use it as an amplitude of magnetic field. All right. All right, so x and t dependence the same. So the difference only in amplitudes and directions of oscillations, directions along which magnetic and electric field oscillates. So these subscripts, amplitude, and the rest is basically the same. It's not a rocket science, it's physics. All right, okay, so that's what you need to remember about electromagnetic wave. And of course, any electromagnetic wave propagates with the speed of light. I've seen a few times only when students use, I think, speed of, or no, I think there was a sound waves, and some students used, no, okay, I forgot what was the story exactly. Okay, it's just they used speed of electromagnetic wave in a completely wrong place. I think with the acoustic waves, right? So it means that it doesn't matter if you have radio waves or visible light, or I know some gamma rays, right? They all travel with the speed of light. So once you see words electromagnetic wave is in the problem, okay, immediately you know the speed. So after that, once we learn how to deal with one wave, of course, we increase complexity, and we started looking at two waves. And we started looking at two identical waves, right? It means that they have the same amplitudes, the same wavelengths, and the same period. So identical waves, but of course produced by different sources. Of course, they're going to interact, these two waves, and we usually use this fancy term, which sounds really nice, cool, interference, right? But it's just a meaning they just interact. And of course, as a result, at some points we can have zero amplitude of the resultant wave, and at other points amplitude will be doubled of the resultant wave, right? So, okay, so we derived conditions. Derivation was a little bit lengthy, but at the end of the day, you just need to use these conditions and nothing else. So you just need to look at the phase difference of two waves, which is 2 pi over lambda times delta r. Delta r, it's a path length difference. It's an additional distance that the second wave has to cover on the way to the point which you analyze in terms of interference. And then plus delta phi naught, the inherent phase difference. There are usually a few situations, right? If the problem says that sources are in phase, it means that the inherent phase difference is 0. So if you look at the snapshot graph at t equals 0, you will see both sources produces sine function, for example, right? So exactly the same, right, two functions. But if the problem says, okay, sources are out of phase, it means what? It means that if you look at the snapshot graph, for example, at t equals 0 at the initial moment of time, you will see this situation. First source, let's say, produces sine function, but the second source produces minus sine function. So the phase difference between them is pi, right? So again, sources in phase, delta phi naught 0, sources out of phase, pi. Or sometimes problem can actually give the initial phases of both waves, and then you just need to subtract in order to find the inherent phase difference. Because what is inherent phase difference? It's a phi 1 0, okay, phi 2 0 minus phi 1 0. Right? Okay, so and then if you calculate it all, and then if you're getting this condition where m is an integer, it's not a mass, just an integer, 0, 1, 2, 3, and all the way to infinity. So if you're getting this condition, at the point which you discuss will be constructive interference. If you're getting this condition, destructive interference. If you're getting something between them, it means that at that particular point, amplitude is not going to be doubled, is not going to be 0. It will be something in between, right? So also possible situation, right? Okay, so this is the picture. For example, two speakers, right? R1, R2, right? We discussed it just recently. And yesterday in the lecture, we spent the whole lecture discussing double-slit experiment, which is basically interference of light. It's exactly the same stuff, but in the case if we have two light waves interacting. And these two light waves were produced by two slits, slit number 1, slit number 2, and this double slit system is illuminated by a laser light. It must be a laser light. The source must be reasonably monochromatic, right, in order to observe this phenomenon. And then as a result, of course, you have this interference pattern with constructive and destructive interference, but since it's not very practical, it's not that simple to find this constructive and destructive interference here in the empty place, right? So it's much more convenient to put a screen and see those bright and dark spots on the screen, just from the practical point of view, right? So basically, that's the system, and we just grabbed these conditions and adjusted them for the screen. So you can find position of the constructive spots with constructive and destructive interferences, bright and dark spots, relative to, I don't know, the center of the screen, right? And we derived this formula. Again, derivation was reasonably lengthy, although not complicated, but at the end of the day, we just need to use this formula in order to solve problems like this, nothing else, right? So where m, again, it's an integer, the same integer, right? Lambda wavelength of the light, L distance to the screen from the double slit, and D is the distance between these slits. Right. So that's what we discussed after the second midterm examination. Okay, so that's the review, and now let's start looking at the problems. So from the very beginning, let's start discussing magnetic forces. Okay. Keep this over here. And so first, conceptually, let's discuss directions of the magnetic force. And let's look at this. You know what? Let me label it as 1, problem number 1. Okay, so let's assume that we have a wire, infinitely long wire, right? With the current, let's say current flows that way, I. And we have 4 point masses, I know, electrons and protons, for example, right? Let's say we have 2 negative charges. Let's say here's one, here's one. We're going to discuss them one at a time, but I want to draw them immediately. All of those charges, and here we have 2 positive charges, right? Plus, plus. Okay, so this is the system. Again, basically 4 parts of the system, and we want to find direction of the force acting on all of these point masses, right? Okay, so first of all, we need to find magnetic field, right? Of course, this current, this wire with the current, it's an infinitely long wire, of course, produces magnetic field, and we know how we can find a direction of the magnetic field, right? Right-hand rule number 2, right? Outstretch your thumb in the direction of the current and curl your fingers around the wire. So as a result, above this wire, we're going to have fingers out of the board. That's dot. So here we're going to have dots. Okay, let me use black. So dots, dot, 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 dot. And of course, below we're going to have crosses. So these are our magnetic field, B, right? Okay, so now once you know direction of the magnetic field, let me check if I got the same. Yeah, of course. All right, now we can find direction of the magnetic force. So of course, it's a fundamental equation, QV cross B, right? Okay, and so now let's start. For example, let's start with this positive charge. It's a proton, for example. So first, V cross B. Right-hand rule number 2. Yeah, they have to move. These charges have to move. Okay, I need to show direction of the motion, because you remember I told you everything in the world of magnetism must move in order to, for example, produce magnetic field, or in order to experience magnetic force acting on the charge from the magnetic field, right? So everything must move. So these charges also must move. Okay, so let's assume that this charge, okay, let me grab my notes. So this charge moves this way, V. Then this charge, let's assume, moves that way. Then this charge moves in this direction. And the last one moves towards the wire, right? So these are velocities. Okay, now everything is on the picture. Okay, so now right-hand rule first, V cross B. First charge, V, that way you remember right-hand rule. First, you'll need to align your hand along the first vector in the cross product, then orient it in such a direction so that you can bend your fingers in the direction of the second vector in the cross product. In our case, V that way. Then B is out of the board, so I have to position my hand like this. So V cross B, and the cross product of V cross B is down. So let me show that V cross B is down. It's a V cross B. And then you remember that additional half a step. After you find direction of V cross B, look at the sign of the charge. If charge is positive, that is the correct direction for the force. In our case, charge, yes, is positive. So that is also direction of the force. Okay, so now let me show that this is direction of the force. Okay, now let's move to the second charge. This, so the velocity is up. Then I need to orient my hand like this so that I can bend my fingers out of the board, because that's the direction of the magnetic field. So V cross B, so cross product V cross B is to my right and your right. So this will be direction of V cross B. But it's not the end of the story, because now you need to look at the sign of the charge. And not quite often, but sometimes students forget about that on the exam. I see it almost every semester. So V cross B that way, but the charge is negative, so it means that we need to flip that direction to the opposite one. Force will be to the left. Okay, let me mute my speakers on my second computer, because it keeps doing something and sometimes making noises. Okay, good. Computers like now have their own minds. They do something all the time behind your back, right? Right. Okay, so that's the direction of the force. Let me check if I'm getting the same. Yeah. So now let's do this charge. Again, V that way, B now is into the board, right? So I have to position my hand like this. First V, then B, right? And then V cross B, direction of V cross B is down. That's only V cross B. Let me show it. V cross B is down, but again, it's not the end of the story. After that, you need to look at the sign of the charge. And this charge is negative. So as a result, you need to flip this direction in order to find direction of the force. So force is up. Okay, let me check if I got the same. Yeah. And now the last charge. V is up. All right, then magnetic field is into the board. So again, V cross B. So you have to position my hand like this, right? V cross B. And the cross product, V cross B that way. And additional half a step, since charge is positive. So that is the correct direction for the force. Direction of the force and direction of the V cross B are the same. So in this case, that is direction of the magnetic force. So something like this, from time to time, I give on the exam. Of course, I can change direction of the current, or magnetic field can be produced by something else. But again, it's all about finding the, applying that formula properly. Right? And right-hand rule number 1, where you need to find the cross product, it's a must. Everyone must know how to use that. Right? Otherwise, you'll have troubles on the exam. Right? Okay, so that's basically a conceptual question, but I present it as problem number 1. Now let's look at the problem number 2. Okay, I need to erase it because problem number 2 will be longer, will be significantly longer. Again, guys, if something is not clear, if you need more explanations, tell me. Okay, now let me erase this. So now, problem number 2. So what do we have here? Okay, so we have a wall. Okay, I'm trying to estimate the amount of space I might need. 2 springs. One is here. The second one is here. Then there is a wire attached to these springs. Right, so let me draw it like this. And with a current, right? We can have a current here. Okay, so current, we know direction of the current, I, this way, down. Then this whole thing is exposed to the external magnetic field. Magnetic field produced by something, we don't know, maybe I don't know, permanent magnet. And direction of the magnetic field is represented by dots, dots out of the board. Right, so let's say dot, dot, dot. And this magnetic field only, there's this magnetic field only between these two lines. Okay, so above this line there is no magnetic field, and below this line there is no magnetic field also. So magnetic field only between these two dashed lines, right? And we know the width of this, the length of this area where there's a magnetic field. L is 20 centimeters. Okay, let me write L, right? And I will write here. So L is 20 centimeters. Right. Okay, spring constants are given, and springs are identical. So spring constant is 10 newtons per meters. Right. Okay, so now what's the situation over here? If there is no current in this wire, we know that this wire will be in the equilibrium at this position. Okay, let me show it. Right, and let me write it. It's equilibrium when I equals 0. If there is no current in the wire, this wire will be positioned over there. Basically, that equilibrium is determined by these springs. Right? Okay, let me introduce coordinate system immediately, since I just mentioned about that equilibrium. So let me align x-axis along that direction. And of course, I will position my origin at the place where wire is when there is no current. But once you turn the current on through that wire, what happens? So now we have a current exposed to the magnetic field. Current exposed to the magnetic field is going to experience magnetic force. And as a result of that magnetic force, this wire gets displaced to this new position. This is new equilibrium when current is on. And we know this compression, the amount of compression. So let me write it, show it first somehow on the picture. Maybe you know what, let me show it like this. So this distance is delta x, and that compression delta x is given. I don't remember the number. 1 centimeter. 1 centimeter. Okay, another piece of information which I forgot to mention. The strength of the magnetic field is given, B, and that is 0.5 Tesla. B, 0.5 Tesla. Okay, so now what's the what we need to find here? The value of the current. So this device, if you look carefully, can be basically used as a current meter, amp meter. Of course, probably not the best one, but look, if you calibrate this x-axis properly, right? So if you, for example, drive the current, I don't know, 1 amp, of course it will be, this wire will be displaced by a certain distance. Okay, so label it. So at this, if the wire at this point, it's a 1 amp. If current 2 amp, wire gets displaced to this point. Okay, put here 2 amps and so on. If you calibrate this axis, you can use it as a amp meter, right? Okay, so that's basically a very crude amp meter device. Okay, so that's the situation, and so now what can be done in order to find the value of the current? You know what, maybe first I will, okay, I explain it. All right, so I'm not going to say it, but remind you, so this is the equilibrium for the wire when current is 0, and this is the new equilibrium when the current is on. Right? So what can be used? We need to start from sort of from some fundamental equations, right? And from there, we can get in the right, start moving in the right direction. We have equilibrium situation, right? Static equilibrium. You remember in physics 1, at the end of physics 1, you solved plenty of problems about static equilibrium. So you try to stabilize some beams, some ladders against the wall, and so on and so forth. So this is effectively that type of problems. But in physics 1, you had which forces all the time? You had frictions, you have normal force, you had gravity, right? You had all those forces which you had in the in mechanics. This is effectively the same situation, but one of the forces is electromagnetic. In this case, actually, it's a magnetic force. Otherwise, it's a problem from physics 1. But in this case, the nature of one force is a magnetic force. It's magnetic. Nature is magnetic, right? So what did you use in physics 1 in order to solve problems like those? Quite often students don't remember, but we already used this idea at the beginning of the semester. Now let me repeat sort of my explanations. Look, guys, which law, fundamental law, can be used to describe motions of any classical system? No restrictions, but of course classical system. I know some object is... Yes, exactly. Newton's second law. That's the idea of the Newton's second law. It's not just F equals ma. No, it's insulting. It's a fundamental law which can be used to describe motion of any classical system in the universe. Galaxies are moving, you can apply Newton's second law. Cat is running, you can apply Newton's second law. Any, no restrictions. So in this case, we don't have motion, but no motion, it's a special case of a motion. And the same equation can be used to describe the case when there is no motion. So it means that we can grab our beloved Newton's second law and apply it here, but we have to demand that acceleration equals to 0. That's the beginning of the solution. And it's a typical beginning for any problem about static equilibrium. You just grab Newton's second law, put acceleration to sleep to 0, right? And from there, solution follows immediately. So let's do it. Okay, so let me write something which I have over here. So Newton's second law, let me write so Newton's second law, but in this case, no motion. For the case of no motion, right? So sum of the forces equals mass times acceleration, and as we just discussed, acceleration equals to 0. Okay, I didn't put a vector sign, although I can put, but in this case, everything is in one direction along x-axis. So all the, if a vector in the positive direction, I will just, positive x direction, I will just use plus. If it's in the opposite direction, I will use minus, right? So I'm not going to write a vector form, right? So beginning of the solution is over here. Net force acting on this wire, that's our moving object, okay, stationary. Net force on that wire must be equals to 0. Right? Okay, so now we see what needs to be done. Now we need to identify all forces and write them properly. Okay, identifying of the forces. Obviously, there will be two spring forces. Since springs both are compressed, of course, they will push the wire towards this equilibrium, right? So both of these spring forces will act that way. F spring, did I label it 1? Yeah. Spring 1. And the second also act in this direction. Let me label it as F spring, wait, it's a 2. F SP2. Okay, so these are two forces, but of course not enough. Of course, there will be magnetic force. All right, since we have current exposed to the magnetic field, there must be magnetic force. Let's quickly check what's the direction of the force. Of course, we see that magnetic force must point that direction in order to balance these two spring forces, but let's do it properly using the cross product, right? Okay, we know direction of the current. Current is down. So in this formula, direction of L, down, because direction of current determines direction of L. Right. Okay, so now magnetic field is out of the board. So right-hand rule. First, direction of L down, so I need to position my hand down. And magnetic field is out of the board, so I have to position my hand like this. So I can bend my fingers towards you. So as a result, my thumb gives me direction to the left, right? Okay? Direction of the magnetic force is to the left. So that's F sub m. That's our magnetic force. Basically, what I've just done, I drew a free body diagram like you've done in Physics 1 gazillion number of times, right? But again, the only difference that one of the forces has a magnetic nature. Okay, so now we need to write this equation properly, taking care of the directions. These two forces, since they point in the positive x direction, that's why I introduced coordinate system, because I need to define positive direction. So as a result, I can write so F spring 1 plus F spring 2, and magnetic force points in the negative x direction, so it must go into the equation with minus. So minus F magnetic, and it must be equal to 0. They must balance each other out, because this object is in static equilibrium. Of course, now we need to write explicitly expression for the magnetic force, and again, it must come from that formula. We just used it to find direction of the magnetic force. Now magnitude. So Fm, let me first write the formula in general. So it's a IL cross B, right? And so direction first to the left. Again, it's a right-hand rule, number 1. And then magnitude. We all know how to write explicitly magnitude of the cross product. So Fm equals to I, L, B, and the sign of angle between vectors L and vector B. Vector L, down, because again, it's determined by the direction of the current, and B is out. Down and out, the angle between these two directions, 90 degrees. This is current, you see, down, and this is magnetic field, 90 degrees. So over here, I have to write 90 degrees. So of course, sine of 90 degrees is 1, and we're getting ILB. ILB. So that's the magnitude of this magnetic force. Okay, so now we just need to plug it in. And of course, spring forces, right? So you remember F spring equals to K. Okay, you know what? It's absolute value basically, right? Because we know the direction, so we already took care of everything. We just need to use the absolute value of the Hooke's law, K delta X. K times delta X. And delta X is given. We know by how much those springs are or were compressed. Right? Right. So now back to our equation. So we'll have K times delta X. It's this spring force plus the second one. Again, they're compressed by the same amount. They have the same spring constant. So K times delta X, K times delta X, and minus ILB. ILB. And it must be equal to 0. So given, that's our unknown, given. One equation, one unknown, basically now at this point we just need to solve for I. Okay, let me rewrite it one more time, so combining this. And maybe moving this term to the other side. So it will be 2K delta X equals to IL times B. Okay, this can be easily solved for I. So it will be 2K times delta X divided by L times B. Okay, so that's the expression which can be used to find the value of the current. Okay, let me check if I got the same in my notes. Yeah. So I'm not going to plug numbers. Numbers are given, right? So I will just write down the answer. It is equal to 2 amps. Again, if you, as I told you at the very beginning, if you calibrate this x-axis properly, so that's amp meter. Maybe not the best one, but can be used. Again, if something not clear, say it. So the next problem I'll usually skip, but it will be in my notes if you want to practice. This is more about cyclotron motion. Okay, you can look it by yourself. Okay, so now, so we practice this, and now, so next in line, Faraday's law. Let's look at the Faraday's law. So I prepared first 2 conceptual questions and then a problem. Okay, conceptually, and in problem number 3, we have 2 conceptual questions. Right. Okay, so let's start with this. We have a ceiling. You know what, let me make the ceiling long. And 3 loops. Basically like, I want to say pendulums, but they're not completely pendulums. Okay, let me just draw them, and then you will see. All right, so the first pendulum, again, it's not completely correct. Okay, so we have a hoop connected to the cord and attached to the ceiling, right? So as a result, this hoop can oscillate back and forth. Okay, can oscillate, right? And let's assume that this whole thing is exposed to the magnetic field, uniform magnetic field for simplicity, right? And dots. Okay, so it means out of the board. So dot, dot, dot. So this is magnetic field. Oi. Right, and over here, right? Let me add a few more dots. So that's B. So, and this loop basically like oscillates. So we need to answer the question, are we going to observe any induced current, induced EMF in this oscillating loop? Right. No calculations, we just need to discuss that conceptually, right? So, so in order to, okay, let me write underneath over here somewhere. Yeah, you know what, let me write it here, so in the corner. EMF equals minus rate of change of the magnetic flux, right? So, one of the universal laws. Okay, so we just, in order to figure out if current is induced, we need to look at the flux. What happens to the flux? If flux is constant, no induced EMF, no induced current. If flux is changing, then yes, current will be possible, right? Okay, so now this situation. So in order to find out what's the story with the flux, of course, you remember flux, it's a B, A, and cosine of angle between them, between these 2 vectors, B dot A. So what happens with B? As this loop oscillates? Nothing. The loop goes through uniform magnetic field. At any point of the loop, magnetic field is exactly the same. It doesn't change in time. So it means that magnetic field is constant. So magnetic field is constant. Then what about area? Area of the loop, also we don't distort the loop. Area of the loop stays the same. Area also constant. And then what about angle? Angle, it's up to you. You can position your area. Yeah, angle. Angle, it's up to you. If your area vector is out of the board, angle will be 0. If your area vector is into the board, angle will be pi, but in both cases, angle is constant. So as a result, flux is constant, and as a result, EMF equals to 0. So in this case, no EMF, induced EMF, no induced current. So in this case, we cannot produce the current. We cannot produce current. Now, the second situation. What if we have a similar story? I have some rope first, and then there is a, you know what, let me use just a spring. And then the loop. And we assume that there is no motion in, actually we can assume even that, but in the problem assumes that this loop only oscillates up and down. So there's no swinging from side to side. Okay, let me show that. So in this case, loop just oscillates up and down. So the same question, are we going to get any EMF or an induced current? Speculations exactly the same like in the first case. As loop moves up and down, magnetic field stays constant. We have uniform magnetic field. Area, again, we don't distort the shape of the loop. So area is constant. And again, angle is constant. Again, it can be 0 or pi. It doesn't matter. So in both cases, in this case, exactly the same speculations can be used, right? So it can be applied for this case, and it can be applied for that case. So for both situations. Right. Now, the last. What if we have, how should I draw it? Okay, this way. What if we have, again, the cord? We have a loop, but now motion is this. So what if we turn that loop around a vertical axis? Something like this. We almost dropped it. So here, story, of course, is completely different. So first, what about magnetic field? Magnetic field is still constant. As you move this, as you spin this loop, you cannot change magnetic field, right? It would be too much. Right? Magnetic field is produced by something else. Then area of the loop still constant. It's still the same. As you spin, you don't change the area of the loop. But angle, no, angle is completely different now, right? So as you turn it, first let's say this is the area vector. So let's start from the point when area vector is towards you. Right. So it's in the same direction as the direction of the magnetic field. And then as you start spinning, so first let's say 30 degrees, 45 degrees, 60 degrees, 90 degrees, 120 degrees, 180 degrees, and so on. As you spin the loop, angle changes non-stop, keep increasing to infinity, right? 360 degrees, 720 degrees, 1000 whatever degrees, right? So angle changes all the time. As a result, angle changes, flux changes as well. So angle changes. Okay, I assume that increases, right? As a result, magnetic flux changes, and EMF is not going to be 0. So induced EMF will be produced, and of course, as a result, also induced current is also not 0. So in this case, yeah, current will be produced. It's an example of a simple current generator, right? Basically, that's the idea behind current generation in any power station, right? Of course, this is oversimplified, but physics is the same, idea is the same, angle changes, right? Okay, so just refreshing stuff which we discussed in our classes anyway. Okay, so now that was the first part of the problem 3. Now the second part. Okay, I'll just separate it with a big line. And now the second part. Maybe I can put, let's say, part A, and now that's part B of problem 3. So now we have this situation. What if we have an infinitely long straight wire with current I? Current is, I think, constant. Yeah, steady current. Then there are two loops. Okay, we will discuss, of course, one at a time. First loop will be on this side and moved, let's say, up, straight up. Second loop will be here and moved to the right. We need to discuss again the presence of the induced current or induced EMF, which is the same, right? So, first situation, a loop is moved up. Let me use green color. So that's direction of motion, and the second loop will be here. And this loop will be moved to the left. To the right, sorry, to the right. So let me call this loop, let's say loop A, for example, so we can distinguish which loop we're talking about. So loop A, and this will be my loop B. Right. Okay, so first loop A. Again, the same. We need to start with we need to start looking at the magnetic flux. EMF equals minus negative rate of change of the magnetic flux. So what happens with the flux? So again, so magnetic flux equals to BA and cosine of angle between them. So in this case, again, as you drag this loop, and current is constant. First of all, what should I start with? We need to find the direction of the external magnetic field, right? Which produces this magnetic flux, right? As usual, right? Okay, so of course we can find that applying right-hand rule number 2. Outstretch your thumb in the direction of the current and then curl your fingers around the wire. So around the wire, so on that side, fingers out, dots, bunch of dots. And of course here in crosses. Okay, I will use blue. So dots, right? So that's B, and on this side, crosses. And of course, the magnetic field extends all the way to infinities, right? But enough. All right, so that's magnetic field, and now we need to look what happens with all these three parameters. B, external. For the loop A, as you drag loop up, parallel to the wire, what happens to the magnetic field? Magnetic field stays constant in time, right? Of course, within the loop, here magnetic field is stronger, slightly stronger than, for example, at this point of the loop, right? But we're interested in what happens with this magnetic flux in time. So if there are differences in the value of the magnetic field from the point to point, who cares? We need to know what happens with that magnetic field in time, not in space, right? But in time, since we tried to change something in time by dragging this loop, but we're dragging up, and as a result, in time, magnetic field within the loop stays the same. So magnetic field in this case is constant. So, right, so B is constant. Of course, area is obviously constant because again, we do not change the shape of the loop. Angle, again, it's up to you, but anyway, it will be constant, either 0 degrees or pi. Again, it depends how you align your area vector. If it will be out of the board, 0 degrees. If it is into the board, pi, but anyway, in both cases it's constant. So angle is constant. So as a result, flux is constant. Okay, I should have started writing slightly earlier. Right? So flux is constant, and as a result, EMF equals to 0. Right? So no fun stuff. Current is not induced current is not going to be produced in this loop in this case. Okay, so now case B. So this situation, if we move loop away from the wire. Okay, now the story is completely different. Okay, not okay, almost completely different. Area and the angle, they're still constant. But magnetic field now changes in time. So we move the loop. So when the loop was here, magnetic field within the loop was kind of stronger. As you move slightly farther away, what happens with the magnetic field strength as you move farther and farther away from the wire? Of course, magnetic field is going down, right? And if you move to the infinity, of course, it will be almost 0. So as you move the loop that way, magnetic field is going down in time. So in this case, B is decreasing, right? Area is constant, angle is constant, and as a result, magnetic flux is going down. And at this point, once you found out what happens to the magnetic flux, okay, probably I should have added subscript M. Right. Just trying to save space, right? All right, so now we need to, okay, start using Lenz's rule. Flux is going down. It's the second case. So as a result, current will be driven, induced current will be produced, and in such a direction so that induced magnetic field within the loop will be in the same direction as the direction of the external magnetic field. So the system becomes supportive, like Florence Nightingale, right? So now, as a result, I can write that B induced will be in the same direction as B external. The loop doesn't like when flux changes. In this case, flux is dying. Right. So now it means that within the loop, I can draw the same direction, bunch of crosses, representing B induced. So these are directions of B induced. Now right-hand rule number 2. So crosses, it's into the board. So I have to position my hand like this in order to match that direction. But again, if you are positioned like this, it will be out of the board, which is wrong. This direction. I mean, this is the correct position of my hand, and then my thumb gives me correct direction of the current. So which is clockwise direction. Okay, let me check my notes. Yeah, clockwise direction. So as a result, I induced is in a clockwise direction. So clockwise, it's this way. So it's I induced. Okay, so we just practice the second option of Lenz's rule. Right. Okay, so sort of conceptual examples of applications of the Faraday's law. Now let's look at the problem. So where we'll have to actually calculate EMF and of course apply Lenz's rule. Right. Okay, so now I need to erase, and that will be problem number 4. And so what do we have here? Okay, so square loop. Again, exposed to the magnetic field, right? Some resistance is given. And in this case, the value of the magnet, and of course, yeah, exposed to the magnetic field, and the value of the magnetic field is going to change. And we will have to find the the value of the EMF and current, I think, produced in the loop, and the direction of the current. Okay, so let me start with the picture. Okay, so I'll draw it here. Yeah. Right. So, okay. This will be a loop. Then resistance is in this part. Let's assume that the rest of the loop doesn't have resistance and only significant resistance in this part of the loop. I don't know, for example, let's say this is, I don't know, 1 kilo ohm resistance. It has this 1 kilo ohm resistance, and the resistance in the rest of the wire will be 0.1 ohms. Of course, you can assume that this doesn't have resistance, and resistance will be only here, right? So you can assume that wire doesn't have resistance, an ideal wire. Resistance is given 10 ohms R equals to 10 ohms, right? Then geometry is given, size of this loop. So this size, actually it's a square loop, but I will use different symbols. I'm going to label this as B, 20 centimeters, and A also 20 centimeters. A 20 centimeters. Of course, you realize at a certain point you will have to convert these to meters, 0.2 meters. Then, okay, it's exposed to the magnetic field. Magnetic field is represented by the dots, means into the board. So magnetic field. So that's B. Okay, so now let me write. So we have a loop, 0.2 meters by 0.2 meters, resistance of 10 ohms. Then magnetic field. Oh, magnetic field, there's a plot showing how magnetic field changes in time. Okay, so I need to erase this. Okay. So now over here on the right hand side, I will plot this graph. So what happens to the magnetic field? So B versus time. Time in seconds. Okay, it doesn't matter. I will show you what are the units, right? So what happens to the magnetic field? So let's say this is 1.5 units of Tesla. Here, let's say we have 0.5. And so first current, okay, current stays constant up to a certain point, let's say, for example, to this point. And then it goes down to the value of 0.5. And then it stays constant again. Right. So let me show that this level and this stretch of time, this delta t is interesting number, 63 milliseconds. So that's how magnetic field changes in time. What else? Let me check. If I mention everything, yeah, it looks like, yeah. So that's the problem. And now, of course, the question, we need to find induced current and direction of the induced current. All right. So we need to find I induced, because magnitude and direction. Of course, first of all, we need to realize physics. And physics, it's about Faraday's law. We have a closed loop, conducting loop, exposed to the magnetic field. Magnetic field, of course, first it's constant, And then within this stretch of time, magnetic field changes in time. So as a result, flux, since magnetic field changes in time, flux changes. In this case, actually dying. And of course, the loop, which doesn't like when flux changes, of course, will respond with induced EMF and induced current. So direct application of the Faraday's law. Right. So now just a question of diligently applying it for this case, nothing else. Right. Okay, so and you remember we most of the time divide application of the Faraday's law into two steps. First, you can find, for example, direction of EMF, direction of the current, and then absolute value of dphi over dt. Or first, find absolute value, then direction. They're sort of independent, right? So let's start first with direction, because it's more like a conceptually, right? So, and then at the end, we'll just drag numbers, right? All right, so first I will put a bullet and direction of I induced, right? Okay. It will be about Lenz's rule. So first we need to find out what happens to the magnetic flux through the loop. And then we see the steps. All right. Okay, three parameters again, B, A, theta. All right, so B, A, and theta. All right, in this stretch of time, magnetic field is constant. And area of the loop stays constant. Okay, let me first write down information about the area and the angle. Area is constant because we don't change the shape. Angle, again, you can make it 0, you can make it pi, it's up to you. I usually make it 0 all the time. So let me align my area vector into the board in the same direction as the external magnetic field. And just, I like when something is 0, right? I think you agree with me. It's much more pleasant to work with zeros than when something is not 0. So 0, right? And so now magnetic field up to this point in time, magnetic field constant and area constant, angle constant. As a result, up to this point in this loop, magnetic flux constant and induced, and there will not be an induced current. No induced EMF, no induced current. And after this point, again, the same story. EMF will be 0 and current will be 0. But within this delta t 63 seconds over this stretch of time, of course, magnetic field changes and of course flux changes, and as a result EMF will be induced. So we just need to look at this stretch of time. So now, and what happens with the magnetic field? It's going down, right? So as a result we can combine them and we can come up with the conclusion that magnetic flux is dying in time, which is of course loop doesn't like. So pretty much we, again, in the second case, induced magnetic field. So the system becomes supportive, Florence Nightingale, right, helping dying flux. Right. So it means that B induced should be in the same direction as B external, right? It means that within the loop I can draw a bunch of a few red crosses, which represents B induced, right? And after this point, the last step, right-hand rule number 2. Where is my loop? Here it is. Okay, so induced magnetic field into the board, crosses, right, into the board. Yeah, so I have to position my hand like this. Right. So in this case, my fingers matches direction of the induced magnetic field, and my thumb gives me direction of the current, which is clockwise direction. Right. Okay, let me check if I'm getting the same clockwise. So I induced clockwise. But you know what? The problem is phrased in this way. The question about the direction of the current is stated in this form. they labeled this point as point B and this point as point A. And they asked, what's the direction of the induced current through this resistor? Is it from B to A or from A to B? Not in terms of clockwise and counterclockwise in the loop. They framed it in a slightly different way. So, induced current flows from B to A or A to B. Since we just found that induced current goes this way, and in through the loop it will be this way, right? So over here, so it's a I induced and this is I induced. So you see, current flows from B to A, right? Right. So from B to A, right? So this, the question was formed in this way. Okay, so now we know direction of the induced current. Now second part, magnitude. So now, yeah, we need to grab absolute value of EMF and calculate it diligently. So EMF equals absolute value of minus d phi over dt. Of course, minus I can drop immediately because we have sign of an absolute value, right? And all right, so now let me write explicitly magnetic flux. It's a B, A, n times cosine of angle between them. You know what? Since I already picked direction of the area vector, it's in the same direction as the direction of the external magnetic field into the board, so the angle is 0. So let me erase this theta and write immediately 0 degrees, just to save space, save whiteboard. So it will be 0 degrees, and now I can close my bracket. Cosine of 0 degrees, of course, 1. Right? And so what's left? Only B times A. Then we just discussed that area stays the same. Magnetic field, of course, doesn't stay. And you see what we're differentiating with respect to time. Magnetic field changes in time. So as a result, it means what? It means that we can extract area out of the sign of differentiation because it's constant. And any constant can be extracted from the sign of differentiation. Moreover, since area it's an absolute value, area cannot be negative, right? So we can take it even out of the sign of this absolute value. I forgot here to close it. Right. We can take it outside of the sign of the absolute value, right? So as a result, I can write A and absolute value of dB over dt, right? Okay, I hope I didn't skip too much steps, right? But I think it's obvious for your level, since you already, almost everyone went through all calculus. So that's what we have. Now, next simplification. What can we say about the graph, how B changes in time? B changes in time with time, linearly. It's a straight line. So if it's a straight line, and if you want to calculate a rate of change of the magnetic field, it is equal to dB over dt equals to delta B over delta t, right? All right, okay, let me write. Since B versus time is a straight line, of course we can write as a result, it can be written as A times delta B over delta t. We already used this trick many times in this course, right? If you have a straight line, what is this? dB over dt. It's basically slope of this curve. And slope measured using infinitesimally small period of time, dt. Right? But again, since this is a straight line, you can also find the same slope using the finite value of delta t. And the slope will be the same because it's a straight line. It doesn't matter if you use infinitesimally small stretch of time or finite stretch of time. So that's what I wrote. dB over dt equals to delta b over delta t. Right? Okay, so now as a result, finally, we can, because we know the endpoints, final value of b 0.5, initial value of b 1.5, so we can write now this explicitly. Okay, so let me, yeah, I have time. I mean, I have space. I think I should be able. Okay, let me write first a times b. Area, it's a length, b. Okay, width, length, and then absolute value of b final minus b initial. Delta b final is 0.5 Tesla minus initial 1.5 Tesla, and divided by the stretch of time over which this happens, 63 milliseconds. So it's 0.063, right? 0.063 seconds, right? Yeah, that's millisecond. Right. Okay, a and b 0.2 and 0.2, right? So these are given. So I'm not going to calculate. And of course, this difference gives us a minus. But since we have an absolute value, we can drop that minus, because that minus would give us direction of EMF, but we already found direction of EMF. So now we're no longer interested in that information. So let me write the value of EMF. So it will be 0.6349 what EMF, just a volts, right? I use ridiculously large, larger number of significant figures because it's not the final result. The question is about current, so I will round it off to 2 sig figs when I get to the current. But for now, I usually prefer to keep larger number of sig figs. So now, once you know EMF, again, EMF produced in the whole loop, right? So now you know the total EMF, you know the total resistance. Almost done. So now I induced equals to EMF divided by the resistance. So, and resistance is 10 ohms, 0.6349 volts divided by 10 ohms. Whew, so it will be 63 milliamps. Yeah, 63 milliamps. Now I use only 2 sig figs. All right, 63 milliamps. So that's the answer. In direction clockwise or from B to A across that resistor. Right. So typical example of the problem where Faraday's law must be used. Okay, so it's the time 1 hour 35 minutes, and we're getting closer to the 50% of the material which I prepared for the exam review. Okay, let me step away. I'm blocking it. So enough. 3 examples about Faraday's law, more than enough. So now let's move into the inductance and look at one problem. There are 2, but the second one you can look by yourself. So we have a solenoid, okay, which is a typical inductor, right? And okay, the value of inductance is given, L inductance, right, is given. And current changes through this inductor in time, and initial value of the current is given, final value of the current is given, and we also know how fast that changes happen. And we need to find potential difference across the solenoid. Again, potential difference produced by the solenoid. You remember over here I mentioned about that. It's not produced by the battery which drives original current which changes. No, that's production of the solenoid. Of course, original battery triggered it all. But still, that potential difference is produced by energy saved in the solenoid. Okay, so now let me write what is given. And the picture, probably I will draw the picture here. So we have a solenoid. And a battery which drives an original current. And this current, let me label it I. Okay, I will probably use blue color for that current. So what happens to this current? So that current flows this way, and that's I. Produced by this battery. You know what, let me even show this battery by blue, so that will be connected, that current and this battery. So that current is produced by that battery. Inductance of the solenoid is given L. So we have an inductor. That's my I, capital I, inductor. Some students laugh about that I, but that's how I write it. Okay, inductor and inductance is 280 millihenry. So L is 280 millihenry. You remember units of inductance, Henry. Units of flux, Weber. Inductance, Henry. And, okay, this current changes. How it changes? Okay, it goes down. So let me show that this current is going down. So now let me show how it changes. Okay, so that current I. So I initial E. I sub I initial. 25 amps. Oh, it's quite a current, 25 amps. And then I final is 10 amps. Right. Okay, so that's what happens to this original current, and these changes happens in 360 milliseconds. Delta T equals to 360 milliseconds. Right. So we need to find potential difference produced across the solenoid. Delta V. Okay, explanations. Across the solenoid. First, we will try to get information about this delta V, about the sign of delta V conceptually. And then we will dive into the formula, right? Because from the formula you can get it, no troubles, because all information is given. But first I want to get conceptually, because quite often among conceptual questions on the final exam, I give problems similar to this. But of course, in that case, you just need to run conceptual analysis in order to come up with the conclusion about the sign of delta V. Okay, so now let's see. And you remember, again, it's a Faraday's law lies behind the work of the solenoid, or the work of an inductor, of inductors, right? And basically, again, Lenz's rule can be applied. But if you try to apply Lenz's rule for this situation, it's kind of not the most convenient. It's better to adjust it slightly. It's still the same Lenz's rule, but now it's better to state it in terms of current. Over here in the Lenz's rule, the loop, okay, a loop, didn't like or doesn't like when magnetic flux changes. It wants to keep magnetic flux as constant as possible. In this case, it's better to restate that rule in terms of the current. So now the solenoid instead of loop. And the solenoid doesn't like when this original current changes in time. If that original current, which is produced by this battery, stays constant, the loop is complete, oh, not the loop, the solenoid, the inductor is completely happy and it doesn't do anything. It's basically sleeping. In that case, the solenoid is just a useless piece of wire in DC current. But once you start changing current through the solenoid, right? Let's say you have a potentiometer and you start cranking it up. The solenoid will wake up immediately because it has some amount of energy stored inside, and it will start. If original current is growing, the solenoid wakes up and kind of, okay, I don't like that you're growing, that current is growing through me. So as a result, it will produce a potential difference in such a way so that the induced current, sort of the secondary current, induced current, will flow in the opposite direction to the original current to suppress the growth, so that the original current would be as constant as it's possible, right? So if original current increases, the induced current will be flowing in the opposite direction. But if original current, this current, like in this case, is dying, the loop again, not the loop, the solenoid again wakes up and kind of I don't like it, and as a result it will produce potential difference across itself in such a way so that the induced current will flow in the same direction as the original current, supporting it, trying to keep original current as constant as it's possible, right? Again, at the expense of its own internal energy stored inside of the solenoid. Again, as I already mentioned several times, it's basically Lenz's rule, stated in a slightly different way, which is more convenient for the case of an inductor. Right. Okay, so now, based on what I just discussed, so let's see what will happen to the potential difference across this solenoid. Okay, so we see that original current is dying. First 25 amps, then 10 amps. So current is, okay, let me probably write it down. So first let's conceptually. Let's discuss. So I is going down. Solenoid doesn't like it. Okay, let me put it. The inductor doesn't like it. Does not like it. So as a result, it produces potential difference in such a way so that as a result, I induced, again, this induced is produced by the inductor, will be in the same direction supporting dying original flux. Original current. Still use the same word sometimes, like in the typical Lenz rule. All right, so in the same direction as the original current. And now, so now let me show the direction of the induced current. In the same direction, it means that induced current will flow this way. Induced current will flow this way, so it will be I induced. You see the same direction as the original current. Okay, I can show it. So it's basically related to that. Right. So, and now, which potential difference across the solenoid is going to produce this induced current? Because this induced current is produced by delta V, which is produced by the solenoid. So of course, in order to produce this current, again, think about some kind of small effective battery, right, instead of the solenoid. So that battery should have a positive electrode on that side and negative electrode on that side. So it means that over here on this side of the inductor, we have higher potential. Over here, we should have lower potential, right? And again, what is delta V? This is the final point where the original current leaves the solenoid. So this is our final point, right? So this is final point, and this is initial point. So as a result, we can write that V final is larger than V initial. So now delta V, which is V final minus V initial, is positive. So that's the end of conceptual analysis of this situation. So if original current is dying, the solenoid produces the positive potential difference across itself. Again, assuming that the final point is the point where current leaves the solenoid and the initial point where original current enters the solenoid. Right. Okay, so now let's get that mathematically from this formula. Since everything is given, numbers are given, so we can get the same thing. Should be able to get the same thing. So now let's calculate math. Okay, so delta V equals minus inductance and di over dt. Again, this current I, it's original current. Okay, so now, once I came to this point, I realized that one small but important piece of information I forgot to mention. In order to use the trick which we used in the previous problem, which I already erased. Look, I didn't state how this current changes. We know current is going down, but how? Is it going down exponentially or maybe linearly? Of course, every time we assume that all quantities changes in time linearly, because in that case, math is significantly easier, right? Physics is still the same, just mathematically situations where quantities changes linearly, easier to explain, right? Easier to describe. Right? Okay, so let me write. Since I changes linearly, so now let me write it here, changes linearly, right? Again, we can use the trick which we used already many times and just 5 minutes ago in the previous problem. So I can write it as a result minus L and delta I over delta T. But again, it is only correct when quantity changes linearly in time, right? Okay, so now almost done. Now we just need to plug values. Minus 280 millihenry, it's a 0.28. 0.28 Henry. Then delta I, again, every time, whenever you see delta, it means the final value of something minus initial. By definition, that's what delta is. So it means that I final is 10 amps, initial minus 25 amps, right? And divided by the stretch of time. Stretch of delta T cannot be negative, right? Time machine hasn't been invented yet, right? Only Hollywood invents stuff, right? In Back to the Future, right? So delta T is 360 milliseconds. That's 0.36 seconds. 0.36 seconds. Okay, so now if you calculate it through and look at the sign, you will get minus over here because this is larger. So negative, minus in front. So two minuses are going to give us plus. So we're going to get the positive value, and that's what we ended up with the same conclusion. The same conclusion we got analyzing this conceptually. So what's the value? No, 12 volts. Wow, such a nice number. So plus 12 volts, right? Again, this potential difference is produced because inside of this solenoid, inside of the inductor, some amount of energy is saved in the form of the magnetic field. You remember, like capacitors in the world of electricity, they stored some amount of energy in the form of the electric field. Here, energy is stored in the form of the magnetic field. Okay, so usually, okay, several times already I give a problem like this, and I usually ask for this conceptual analysis, right? Basically, like it's a Lenz's rule adjusted for the solenoid. Again, if current is constant, the solenoid is happy. If current is growing, solenoid wakes up and starts it rebels, right? It starts driving current, induced current, in the opposite direction, right? And then you need to position polarity properly so that induced current can flow in the opposite direction. If, like in this case, original current is dying, again, solenoid doesn't like it. But in this case, the solenoid becomes supportive, right? It produces potential difference in such a way so that the induced current will be in the same direction as the original current. So it's all about these three steps. Right? Okay, so now after inductance, we go to the traveling waves, but basically traveling waves and these electromagnetic waves, it's the same, right? All the same ideas, right? So we will skip that and we will just start looking at electromagnetic waves. Yeah, you have questions, guys? Oh, somebody just...
I have a question.
Okay, good.
The initial current here was 25 and the final was 10. But let's say if we switched them and it was 10 initially and 25 finally, I guess what my question is, the solenoid still doesn't like it.
Yes, again, as I told you, it's like a Lenz's rule. Loop likes the fact that if magnetic flux stays constant. Here, the solenoid likes when current stays constant.
Doesn't like upward.
Yes, it doesn't like changes. It doesn't like changes. Sort of the way I usually explain it. Of course, it can be described using conservation of energy, but it's complicated, right? So, solenoid wants to have constant current. In this case, if let's say you change numbers, right? Initial 10, final 25. In this case, original current is growing. Solenoid still doesn't like it. But in this case, it rebels, right? Of course, it will try to suppress the growing current by driving an induced current in the opposite direction. So in that case, this induced current would flow in the opposite direction. Right? And in order to produce current like this, of course, this plus should be over here and this minus should be over there. Only with that polarity, the induced current can flow in the opposite direction to the direction of the original current.
And your delta V would be less than 0.
Yeah, delta V will be less than 0, right?
Okay.
Because I can draw if the induced current in the opposite direction, let's say it's I will use green color. If it's this way, right? So which battery with which polarity can produce current like this? Over here we should have larger electrode with plus, and over here smaller electrode with minus. In that case, this sort of effective battery will start driving current this way. So it means that over here we'll have plus and here minus. Right?
Okay.
So this is final point. Smaller potential. Here, larger potential. So subtract this minus that. Of course, you will get negative value. Delta V will be negative.
Okay, thank you.
Okay. And again, based on my experience on the final exam, if I give a problem about this, about a significant percentage of students made mistakes. I would say probably like 30-40% of students make mistakes over here in these speculations. Right. Okay, so now, all right, electromagnetic waves. Yeah, we solved problems about traveling waves, but not much about electromagnetic waves. But again, idea is the same. Except for now, instead of one traveling wave, we have two traveling waves propagating together, right? That happy couple propagating, doing exactly the same together, right? Supporting each other and so on. So, EM wave, electromagnetic wave, EM wave. Okay, let me start with a picture, and probably I'll draw it by hand. Okay, it should be probably enough space. So let's say this is Z. Then X and Y. So you see how I oriented my axis, but it's still a right-handed system. So if you take a cross product of X and Y, you will get Z direction. So it's okay. So then electromagnetic wave propagates in Z direction, and electric field oscillates like this. Right. So that's electric field. Okay, let me draw a few electric fields, electric field vectors. Right. So that's E, red. But of course, electromagnetic wave consists of two traveling waves, electric field and magnetic field, right? So magnetic field, again, oscillates in unison. So they share the same ups and downs, like friends, right? Look, happy couple, right? So it means that maximum is at the same point, zero at the same point, then that way in the same point, then here and here, right? So that's my magnetic field. So let me show it here. B. Then, as I said, this electromagnetic wave propagates in the positive Z direction. So I need to show the vector V. V. Okay, and you remember all these three directions, E, B, and V, must be perpendicular to each other, period. If they're not perpendicular, something wrong with your electromagnetic wave, right? And, okay, additional piece of information. We know that amplitude of this electric field, okay, if I draw this dashed line, this is E naught equals to 9 volts per meter. You remember electric field units, either newtons per coulombs or volts per meters, it's the same, right? You can easily show that newtons per coulombs and volts per meters are the same. 9. So that's amplitude of E. Right, then another additional piece of information, frequency is 1.5 times 10 to the power of 8, I think, right? Yeah, 10 to the power of 8 hertz, which is basically 150 megahertz. It's not that, frequency is not that high, right? It's still, yeah, almost radio waves. High frequency side. So that's it. And now we need to answer a bunch of questions, A, B, C, D. Basically, my goal creating this problem is, at the end, I want to write mathematical expressions describing electric field and magnetic field. So we will have to find some, wavelengths, then maybe something else and something else. Eventually, we will have to find k omega and amplitudes, and I want to write mathematical expression describing traveling wave of the electric field and magnetic field at the end. But before I start telling you what needs to be found, let me ask you. We're still dealing with traveling waves, right? And you remember two types of graphs which we usually use in order to analyze wave, because it's a function of two variables, x and t. And for a brain of a normal, regular human being, it's difficult to imagine at the same time what happens in time and in space. So usually as a result, we usually try to fix, for example, time and observe what happens in space. In that case, if we fix time, its graph is called a snapshot graph. If you fix x, space coordinate and see what happens in time, it's called history graph of that particular point X, right? In this case, this graph, what type of graph? Since here we have Z actually I can show it's in meters, right? In meters. So this is basically a photograph of the wave. Of course, if you can take a photograph of electromagnetic wave, of course you cannot take it, right? But let's imagine, right? So effectively, it's a snapshot, it's a photograph, it's a snapshot graph. It happens, I don't know, at a certain moment of time. Let's say t equals 0, for example, right? It's a snapshot graph. So let me just state this. So it's a snapshot graph. So at a certain moment of time, we can assume, for example, let's say for simplicity, t equals 0. Right. Okay, so as a result, again, before we start solving problems, right? So what can you tell, for example, about this distance from this crest to this red crest? What is that? In a snapshot graph, distance between crests, it's a wavelength, right? If you have a history graph, yeah. If you have a history graph, of course, distance between crests in a history graph, it's a period, right? But here it's a wavelength. But on the graph, wavelengths, information about the wavelengths is given, so we will have to find it somehow else. Right. Okay, so I just wanted to discuss some preliminary stuff before we dive into this tons of questions, finding this on that. Okay, so first question, what is the first? Let's find wavelengths of this electromagnetic wave. So first part A, we need to find wavelengths. Wavelengths, you remember, it's a spatial periodicity. Spatial periodicity of the wave. Basically, it's a distance over which wave reproduces itself in space. Okay, so what can be done in order to find wavelengths? It's a spatial quantity. We have information about temporal quantity. Frequency, it's a temporal quantity, right? And you remember, temporal quantity and spatial quantities are connected through, where is it? Through the speed of the wave, right? So now over here, we have information about the frequency f. We need to find lambda. So if we know the speed, we can find the wavelength, right? And again, as I told you, whenever you see words electromagnetic wave, it should tell you immediately that the speed is given, is known, not given, not tacitly given, right? It's the speed of light, because again, every semester on the final exam, I see a few students struggling, right? So they keep asking, so what's the speed? What's the speed of the wave? And I kept telling them, okay, I cannot tell you. You're supposed to, your brain's supposed to realize that immediately once you start reading the problem. Usually after 10-15 minutes, they get that, right? Okay, so, let me state it. So V equals C equals 3 times 10 to the power of 8 meters per second, right? And so now once you realize that, then finding the wavelengths, it's a piece of cake, right? So now, as a result, wavelength equals speed of light divided by the frequency. 3 times 10 to the power of 8 meters per second divided by 1.5 times 10 to the power of 8. Okay, hertz, it's 1 over seconds. 1 over seconds. As a result, seconds gets cancelled and we'll have only meters left. And, numbers are nice. Probably I picked on purpose. 2 meters. As a result, we're getting wavelengths of 2 meters. Okay, it's ugly meters. Let me change it. Then, wave number B, K. Okay, part B, but we need to find K, wave number. Again, you remember wave number. What is wave number? It's effectively spatial frequency. How fast wave oscillates in space, right? And by definition, basically, that's how we introduce it. It's a 2 pi over lambda, and actually I wrote it here, right? Wave number 2 pi over lambda. For most of you, it's a new quantity. You've never seen this quantity, never heard about this quantity before. But in optics, it's a very popular. It's used a lot. K equals 2 pi divided by lambda. Since we just found lambda, again, piece of cake. So it's a 2 pi divided by 2 meters. Units of wave number, just the inverse of meters or centimeters, right? It depends in which frequency range you work. Sometimes, like in low frequency range, in terahertz, microwave range, very often they use 1/centimeters, right? They find it more convenient. But in this case, we will use meters. So it will be what, pi and units meters to the power of -1. So then, what's next? Angular frequency, A, B, C, omega. It's not W, because very often I see students write W. It's not a crime. You can, as long as you define, so your W is angular frequency. But usually you can confuse people who knows physics, right, using W. Okay, it's a omega. All right, and again, by definition, omega is 2 pi over period. Again, it's basically temporal frequency. So 2 pi over TUCK, and omega introduced almost in exactly the same way. 2 pi divided by spatial periodicity, 2 pi divided by temporal periodicity. Lots of symmetry. Okay, so period. Period is not given, but we know how period and frequency, which is given, are connected. Period, it's a 1/f. So, of course, we can write it as 2 pi f. So frequency is given. So it will be, okay, probably I will write in terms of pi. I think that's what I did. Let me check. Yeah, in terms of pi. So 1.5 times 2, it will be 3 pi. 3 pi and times 10 to the power of 8 radians per second. All right. Again, sort of like a convention, whenever people talk about wave numbers, strictly speaking, it's still radians per meters. But again, inside of radians, there is nothing. So quite often people usually write inverse of meters. But whenever people talk about angular frequency, so sort of like a, I had no unwritten convention. Here, people usually say and write radians per second. So now next, okay. So now we have Ks and omegas. Now amplitude. We need to find information. We need to find amplitude of the magnetic field. And again, at this point, again, some students struggle A, B, C, D. Right. So now B not. But as I told you, magnetic field amplitude and the electric field amplitude are deeply connected, right? To the speed of light. Basically, it means that once you know one of those amplitudes, you can immediately write down the amplitude of the other quantity, right? And of course, remember, electric field is stronger than magnetic field. And then just remember that factor through which they are connected is c, speed of light. Okay, so we need to find B naught, so it will be E naught divided by C. So B sub 0 equals to E sub 0 divided by C. Again, it can be derived, but I didn't derive because the derivation basically of electromagnetic waves from Maxwell's equations are very tedious, and I told you in the lecture, so it's not worth of time. So electric field amplitude in the graph is given in the graph. So look at the graphs carefully if graphs are given. All right, so it will be 9 volts per meters divided by 3 times 10 to the power of 8 meters per second. So meters cancelled, and we'll have what? 3 times 10 to the power of -8 Tesla. 3 times 10 to the power of -8 Tesla. Okay, so at this point, we're all set. We have all the ingredients ready to write down mathematical expressions describing electric traveling wave and magnetic traveling wave. Right. Okay, so now let's first write down electric and then magnetic. All right. So it's part E. Yeah, A, B, C, D, E. Right. Okay, so I will start just with E equals I'm leaving some space for subscript. And now, of course, amplitude. Amplitude, again, on the graph. So it's a 9 volts per meters. And then sine. Okay, K. K is, we found. So it's a pi times spatial coordinate. Pretty much, I remember, okay, all spatial information is in the first term. Times, okay, which variable I should I write here? Think for a second, right? Because again, it's the now I'm coming to the points, and that's why I skip the subscript, right? Because at these places, I will again say several times, at these 3 spots, that's the typical places for mistakes. Lots of mistakes. So which variable should I use now? Over here, I see somebody already answered through the chat. Yes, that's correct. So this variable tells us along which axis our waves propagate. Waves propagate along z-axis. Be careful, tons of mistakes at this point. Because usually students get used to that in our pictures we use all the time x, 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 right? Now in this case, it's a z direction, right? So I have to use z. Okay, it's the first place for mistakes. Then sign, which sign should we use, plus or minus? Since a wave propagates in a positive z direction, it means that we need to use minus between these terms. Don't forget about this switch of signs. So positive z direction, it means that we have to use minus over here. Okay, then omega. Omega we found this 3 pi times 10 to the power of 8. All right, so 3 pi times 10 to the power of 8. And, okay, temporal variable, we cannot change time, right? The direction of time, so it's beyond of our reach, right? So time, all the time is here, right? Then initial phase. Actually, in this particular situation, since this is a snapshot graph at t equals 0 and both of the waves goes through the origin, it means that initial phase equals 0. Moreover, most of the time, whenever people work with electromagnetic waves, they're not interested in the initial phase. Because frequencies are usually high, these waves oscillates too fast, and what it does at the initial, what happens with the initial phase, they don't care most of the time, right? So that's why if I ask questions about electromagnetic wave, I usually skip question about the initial phase. But in this case, it's 0, right? So I will just close the bracket. Now, I skipped on purpose subscript over here. And it carries very important piece of information. Which subscript should I put here? Again, tons of mistakes over here. I see somebody typed X. Yes, because look, this subscript tells us along which axis electric field oscillates. A wave propagates along z direction, but electric field oscillates in the x direction. So this subscript gives us that information. So here we have to use x. So this and that point, lots of mistakes. But again, you just need to either, it's given in the problem, read carefully problem, or on the diagram, on a picture like this. In this case, electric field oscillates in the x direction, propagates in the z direction. Transverse wave, electromagnetic wave is a transverse. So this is perpendicular to that. Okay, electric field, mathematical expression for the electric field. Now, magnetic field, I think it's a, yeah.
The subscript on the E is the direction of the wave, not the propagation, correct?
Yeah, direction of oscillations. I emphasize, it's a direction along which electric field oscillates.
Okay.
Yeah.
Got it.
So now magnetic field B. Okay, again, okay, now you know where the typical places for mistakes, and now I will start immediately. Which subscript must be used here? Again, it's a direction along which magnetic field oscillates. And magnetic field oscillates along y direction. In this case, it's a horizontal direction. You see, blue magnetic field oscillates along y direction. So we have to put here subscript y. Okay, then, and of course, then magnetic field amplitude. And again, I don't know why, but plenty of mistakes. For example, several times I gave this situation. Electric field, information about the electric field, plenty of information about the electric field was given. And then I asked to write down expression for the magnetic field. And still, I don't know why, but plenty of students just grabbed amplitude of the electric field and used it as an amplitude of the magnetic field. Okay, because they're connected to the speed of light, and we already calculated, right? So 3 times 10 to the power of minus 8 Tesla. Okay, amplitude of the magnetic field. And again, still, whenever, quite often, almost every semester, if I asked about mathematical expression for the magnetic field, over here for the magnetic field, lots of math. Although this part, sign, and this time and space dependencies, exactly the same over here. Because you remember I told you about this eternal laugh and happy couple, and this couple shares ups and downs all the time together. Why? Because space and time dependence are exactly the same. So this part, sign, with all this stuff inside of these brackets, exactly the same. Just don't think, just rewrite it over here. So the difference between this expression and that expression only, of course, in amplitudes and in these subscripts. Because, of course, these two waves oscillate in perpendicular directions. It's a transverse wave, right? So amplitude we wrote, direction of oscillations are here, is here, and now I will just rewrite exactly the same thing. You don't have to invent bicycle again, right? Sine pi z minus 3 pi times 10 to the power of 8 Tesla. That's it. Again, based on my experience, up to this point, okay, I don't know, almost, okay, not 100%, maybe 90% students do absolutely right. Here, maybe direction of oscillation and this, but with magnetic field, plenty of mistakes. Although it's not a rocket science. These are just traveling waves. Okay, so what else? Yeah, so we done with this problem, right? Any questions? Okay. Then, so enough about these traveling waves, electromagnetic waves, right? Now interference. So what about time? Okay, almost 2.5 hours. Yeah, we still have a few problems to discuss. 1, 2, 3 big problems. Probably 1.5 hours. Okay, I will start erasing this. Now interference. There will be.
I have a question
listen.
about the
Yeah.
interference. So when we choose M, can we choose any number pretty much? Like 1, 2, 3?
M, of course, in general, it's a positive integer. It can be anything from 0 to infinity. All right, but first we will now we'll solve one problem, right? And for that particular problem, for that particular point, there will be a certain m, right? So in general, theoretically, right, m can be anything, right? And each particular m is going to describe constructive or destructive interference at one particular point. For example, let's say we have this interference pattern, right? So for example, let's say over here there is a point, let's say constructive interference, that will correspond to integer m, let's say, I don't know, 22. I'm just making it up, right? Then next to that, first there will be destructive interference point, then another constructive interference point that will correspond to integer 23. Then again, after some distance, there will be another constructive point, which will correspond to integer 24, and then again 25, 26, and so, of course, pretty much this whole space will be filled with these constructive spots with constructive interference, and each of those spots will be described by a unique m. And since you're going to have almost infinite number of those constructive spots with constructive interference, that's why you need this almost infinite number of integers. So each integer is going to describe constructive interference at a particular point.
Okay, so unless the m is given, you can pick any arbitrary integer for
No,
m?
usually, if system is given, most of the time a problem asks about particular point. So you see that point, so can you figure out what's happening at that point, constructive or destructive interference, right?
Okay.
But this time I prepared one additional problem where we will have to tune the frequency, and as a result, at the same point you can have different situations, constructive or destructive interference and so on. It depends on how the problem is stated. But
Okay,
I told you, basically, the situation is, since you have here infinite number of points with constructive interference, that's why we need to have infinite number of m's to describe each point with a particular integer.
Okay, thank you. That makes sense.
Okay, so now let's solve a couple of problems. And I think a few years ago I gave this problem as a quiz when we were in classes, right, for 10 minutes. And then I decided to recycle it and use it in the exam review session. So what do we have? We have two radio antennas. Immediately it means what? It means we're dealing with an electromagnetic wave, right? And of course, if you need a speed of light, if you want to know the speed, it's a speed of light, right? Whenever you know it's electromagnetic wave, you know the speed. Okay, so we have two antennas. Let me write that down in words. So two, radio antennas to emphasize on the nature of this wave, electromagnetic wave. Two radio antennas. And these antennas, generating electromagnetic wave, not the receivers. And the frequency is 300 megahertz. One frequency is given because you remember we discussed interference of two identical waves. It means that they have the same amplitudes, the same frequency, the same wavelength. So if frequency is given of one wave, it means exactly the same frequency of the second wave, right? So it means that we know the frequency of both sources. Then a certain point is given and distances. So now I need to draw the picture in order to show the rest of the information. All right, so let me draw one antenna here. Let me draw. You know what? Let me use green and blue, usually my sort of unwritten convention to use different colors for different antennas. So let's say this is antenna number 2. All right, so let's say this is antenna number 2. And initial phase is given. So this antenna generates electromagnetic wave and initial phase is given. It's I'm talking about this initial phase, phi naught. But in this case, it's antenna number 2. I'm going to add a subscript to phi 20 or 0, whatever. So phi 0, 2 equals to pi. Then the first antenna over here, and so it's antenna number 1, and initial phase 0, 1 equals to 0. So what does it mean? It means that if you look at the snapshot graph at t equals 0, you will see pure sine function, right, which starts at the origin. Right. But this will be shifted by pi. Basically, this will give you minus sine function at a snapshot graph taking at t equals 0. Okay, then the point which we want to analyze over here. Right. How should I? Okay, let me put first point dot, and let me position another person. Okay. That's the observer of the net wave at that particular point. Basically, we need to figure out what happens at that point. Distances are given. So let's say this distance is R2, 5 meters, and the distance from the first one. All right, so R1, 2 meters. Okay, so that's what is given. And I know that person may be standing there with antenna to receive, to see the amplitude of the net electric field at that point. Right. So constructive or destructive interference, let me label that point maybe like point P. Right. So C or D at point P. Let me state it. State the question like this. C constructive, D destructive. Which interference are we going to see over there? And again, you remember what does it mean, constructive interference? You have overlapping, two waves overlap. And of course, if they overlap like crest over crest or trough over trough, of course, the amplitude is doubled. So let's say if amplitude of one wave is 1 meter, the amplitude of the point with constructive interference will be 2 meters. And of course, there will be points where you have a crest of one wave over trough of the second wave. Of course, crest over trough, of course, they're going to kill each other, right? Giving us zero zero amplitude of the resultant wave. And of course, there will be tons of points where you have neither maximum amplitude nor zero amplitude. Maybe instead of 2 meters, okay, 2 not meters. Since we're talking about electric field, volts per meters, right? You will have, I don't know, maybe 1.2 volts per meters, something in between. So that's the point. And now conditions. Yeah, you remember derivation was reasonably complicated, but at the end we just need to use this. Okay, let me rewrite it. So 2 pi over lambda times the path length difference plus the inherent phase difference, and it must be equal to either, if it is equal to m times 2 pi constructive interference. These are conditions. This is condition for constructive, and this is condition for destructive interference, right? And again, if you're getting something in between, yeah, it's quite possible. It means that amplitude will be, I don't know, between the maximum and zero. Right? There are tons of points like that. All right. Okay. So this is the starting point, and now we need to find basically 3 pieces, 3 ingredients: delta phi naught, delta r, and lambda. Right, so let's start one by one. Delta phi naught, the inherent phase difference. And again, delta, why it is called the inherent phase difference? Inherent, it means like property of the system, right? Basically, it means that it doesn't matter which point you're going to consider, this point or that point or that point or this point or here or here, the inherent phase difference will be exactly the same for all those points. Delta r will be different, right? Because distances for different points are going to be different, right? That's why we don't have a name inherent path length difference, because the path length difference are going to be different for different points. But delta phi naught is going to be exactly the same, because that's the property of the sources. Once you pick the sources, once you set them up, inherent phase difference is fixed. And then it doesn't matter which point you're going to consider. Right? And now in these days, right, with the function generators, I work with them a lot, right? So it's so easy to set up the initial phase difference. It's not a big deal. All right, so delta phi naught. By definition, you remember when we derived it, it's a phi 02, the difference between the initial phases, right? So phi 02 minus phi 01, in this case, I gave in terms of initial phases. So pi minus 0, so the inherent phase difference is pi. So basically, they are out of phase. Instead of this information, the problem could have been stated in this way: source is out of phase. And in that case, you're supposed to extract information about the inherent phase difference from these words: out of phase, source is out of phase. Out of phase, it's pi. Okay, but here I gave initial phases. Okay, so now we know this. Now delta R, trivial, right? Delta R, again, it's a R2 minus R1, 5 minus 2. Wait. 5 minus 2 equals to 3 meters. Okay, so first ingredient, second ingredient. Now the last one, wavelength. Wavelength is not given, but frequency is given, right? So how can we find frequency? Since we know the nature of the wave, it's a radio wave, which is electromagnetic wave. It means that the speed of light. It travels with the speed of light. And so we can use again this lambda f. Right. So f will be equal to c over lambda. Oh, no, we need to get lambda, not f. Sorry, we need to get wavelength. Lambda f is given, so it will be c divided by f. All right. So 3 times 10 to the power of 8 meters per second divided by where is frequency? Yeah, over there. So 300 megahertz, mega 10 to the power of 6, and there are 2 zeros in front, so it will be 10 to the power of 8. Oh, nice. It will give us 1 meter. Probably on purpose I picked the numbers. Wait. 1 over seconds. 1 over seconds hertz. Right. Okay, so wavelength is 1 meter. Okay, so now all ingredients are prepared. It's sort of like in cooking, and now we can start cooking, actually putting everything together. This is our pot, and now we need to see the outcome. Right. So 2 pi divided by wavelengths 1 meters. Then inherent, the path length difference 3 meters. Then plus inherent phase difference pi. And so let's see the outcome. 6 pi plus pi, 7 pi. Okay, and at this point, again, don't rush. I was warning in my recitation classes, because at this point, I've seen in the past plenty of mistakes, because the problem is almost solved. And of course, students are rushing to jump to the next problem, and they're rushing to write the conclusion. And they're sort of, I think the logic was like this. It looks as simple as this condition, so it must be constructive. Careful. Yeah, it is as simple, but this is an odd number, 7 number of pi, 7 pi's. Here we have 2 times an integer. It doesn't matter which integer you have. If you multiply it by 2, you will get an even number all the time. You will never be able to get odd number, right? So it means that it's impossible to get constructive interference out of that. So it should be either something in between, or let's try destructive interference, but definitely not constructive. So don't rush at this point, again, based on my experience, right? And of course, when students see that that is a mistake, they kind of, oh, damn it, how come that I made that silly mistake? Just to be careful. All right, so definitely not constructive. So as a result, I will try destructive interference situation. So m plus 1 over 2 divided by 2 pi. Let's see if it works. Again, m is an integer. It's 0, 1, 2, and so on, right? So which m fits this condition? Basically, we will be able to identify that that spot corresponds to this particular integer, right? It's related to the question which I was asked, right? So 0, m equals 0. No. So in that case, we'll have 1 over 2 times 2 pi. It's just pi. We have 7 pi's. 1. 2 over 2, it will be plus 1 over 2, 3 over 2 times 2 pi. It's a 3 pi's. Still too small. Then 2. 2, it's a 4 over 2 plus 1 over 2. It's a 5 over 2 times 2 pi. It's a 5 pi. Not enough. I need to add additional integer. Right? All right, so 3 and so on. So let's try 3. 3, it's a 6 over 2 plus 1 over 2. It's a 7 over 2 times 2 pi. Yeah, it gives us 7 pi. So integer 3 works. So at that particular point, we're going to have destructive interference, and that destructive interference is explained by using integer 3. Maybe next to this point, if you step away slightly, first you will, of course, you will be able to find constructive interference. All the time they alternate, right? So you cannot jump from destructive immediately again to destructive, right? Because amplitude changes slowly, right? So first, if you have here 0 amplitude, net amplitude of the net field, right? Then if you start moving away, of course, amplitude starts growing. So it's something in between. And at a certain point, of course, it will reach maximum, right? Which is constructive interference. And if you keep moving away from this point, of course, amplitude will start going down. So it's something in between, down. And at a certain point, it will be 0 again, destructive interference. And again, if you keep moving, again, it will start increasing, constructive, then destructive, constructive, destructive, right? So, conclusion, we're getting destructive interference. Okay, so this is reasonably simple. All right, that's why I gave this problem as a quiz, in-class quiz, where I usually give like 10 minutes, or maximum 15 minutes. And of course, if students know how to apply, it should be done within a few minutes, maybe like 3-4 minutes. All right. Okay, so now a problem which more complicated, in terms of understanding, but we will spend some time trying to realize what happens in the next problem. I assigned it for one of our last recitation classes, but at least in my classes, I only discuss sort of physical situation without getting through all the gory details. So now I decided to do that. I don't know, maybe in your recitation classes, your instructors managed to discuss this problem. But anyway, I want to repeat it again. So let me erase it, and this will be problem number 8. So what do we have here? 2 loudspeakers. Okay, just 2 speakers. 2 meters apart. Okay, let me start with a picture. Right. Probably I will do it here. I draw the picture. So as usual, I use green and blue for the colors. So let's say the first speaker is here. Let's say it's a green one. Right. And this is number 1. Then the second speaker is here. Right, so that's speaker number 2. The distance between them is given. Some geometry. So let's say the distance between them is L. Okay, L. Okay, let me first write 2 speakers. So it means that we're dealing with acoustic waves. I think in the problems like this in the past, on the final exam, I saw a few students use the speed of light. I think that's what I was trying to recall, what 1 hour ago, right? These are sound waves, right? And the speed of acoustic waves around 340 meters per second, give or take, depends on the conditions, atmospheric conditions, right? All right, so let me write the speed. All right, so V equals 340 meters per second. And so distance between them, L, 2 meters. L is 2 meters. And then particular point is given, which we want to analyze. But analyze for what? I will tell you in a few minutes. So the point in question is right in front of the first speaker. So right in front, and this distance R1, and that R1 is given. R sub 1 is 3.75. 3.75 meters. R2 is not given, but of course let me draw R2 anyway. So that's R2, and it's not given because you can find R2 easily, because this point is right in front of the first speaker. So this is 90 degrees, right? So it's a right triangle. So R2 can be easily found. It's a question just over calculations. That's it. So basically R2 is given. Then we need to have information about the initial phases or inherent phase difference, because at the end of the day, we will have to still use these conditions. Right? So we need to have information about the inherent phase difference. And let me check what is given. Sources are in phase. Basically, in the previous problem, which I just erased, they were out of phase. I gave you initial phases, but they were out of phase. Now in phase, again, whenever you see words sources are in phase, it means that the inherent phase difference is 0. Usually on the exam, lots of mistakes in the questions related to the inherent phase difference. Sometimes students just completely ignore it and try to solve the problem, somehow hiding it, right? And as a result, lots of math. But that's usually stated in the problem. So let me write sources are in phase. So let me write the sources. Okay, speakers. Sources are in phase. Let me underline it twice. And from here, I can write immediately. So delta phi naught equals to 0. So that you would remember. Actually, this arrow overlapped with P. It looks like the P with an arrow down. So what else? I think that's it. Yeah, that's what is given. And now the question. We need to find 3 lowest frequencies at which, at this point, okay, let me label it as point P. So at this point, we're going to have destructive interference, 3 lowest frequencies at which we're going to have destructive interferences at point P. Then part B, 3 lowest frequencies at which we're going to have constructive interference at point P. First, for now, it might sound, what the hell he's talking about? So what does it mean, right? Okay, we will discuss it, and I hope it will be clearer. Right? But first, let me state the questions. Let me confuse you, and now let me clarify what does that mean. Okay, so now let me draw a different picture in order to go into the explanations. Right, so now let's just leave it all this information alone, and now let me separate it like this and explanations. So let me draw something like this. Again, 2 speakers. Now I'll just use the same color. Let's say something like this. Right. So the first speaker, the second speaker, right? And of course, they're going to generate 2 sound waves, right? So the first one, right? So the second one generates its own waves, right? As a result, we have what? As we just discussed when you asked me a question, so about those integers. So pretty much this whole space will be filled with spots where we can see constructive interference and destructive interference, and every time they alternate constructive, destructive, constructive, destructive, constructive, destructive, right? And our point, let's say this is point P, is let's say this is our point P, right? So let's say at this particular situation, a certain frequency is provided to the speakers. Whatever acoustic frequencies are, right? Very low, but I'm not in music, so I don't remember exactly frequencies, right? So let's say certain frequencies are applied to the speakers and they generate the waves at those frequencies. So in this situation, for these frequencies, with this initial phase, with this delta phi naught, let's say we have this distribution of constructive and destructive interference. Let's say at this point we have constructive, then next to that will be destructive, then again constructive, then destructive, constructive, destructive. Over here something similar. Then if you start moving closer, again, it will be, they will alternate. So over here, you will have destructive, constructive, destructive. Pretty much the whole space will be divided into the into these spots with where you can see constructive and destructive interference. So this is the picture when you have these particular frequencies. But what if I attach to my these speakers a tunable source of acoustic waves? Tunable, the key word. These days, at this low frequency, you can easily get them, right? And probably for cheap, right? So, and let's say we have a dial which allows us to tune frequency. Tunable source, let me write. Tunable source. So we can change frequency continuously. Basically, you sit here, you grab this knob and start tuning slowly, right? Let's say increase frequency. Let's say this is our initial frequency, and from this frequency you start increasing F. So let's say we F increasing. Still, I'm trying to describe what happens, right? We are not discussing the solution. I'm just still preparation for the solution, right? Okay, so basically I sit here and change the frequency, and now I want to show what happens in terms of frequencies, right? So what happens once you start tuning frequency slowly? All these spots with constructive and destructive interference, they all start moving like complicated, I know, organism, some creatures, right? So, of course, it will be complicated motion of these constructive and destructive spots with constructive and destructive interference. But let me simplify. For example, let's say that as we start changing the frequency, all these CD will start moving to the right. It means what? If I change the frequency, so this is the initial frequency, right? So if I change frequency slowly, right? So this destructive after short range of frequencies, this destructive, okay, this is our spot, this destructive interference will move to that spot. So now at that particular frequency, at point P, we're going to have destructive interference. So initially we have constructive, so let me write that down. So over here on this, so let's say we have F first frequency with constructive interference, 1C. Basically, let's assume it corresponds to integer number 1. So it's initial situation, right? And then once I change the frequency slightly, right? So now this destructive interference come into this spot P, into this point P. So now I will have first destructive at this point. We're going to have a destructive interference, and let me call it number 1. So this destructive interference corresponds to integer number 1. Then I keep changing this frequency, so now these spots will keep moving through our point P. And of course, after short frequency range, this constructive interference will come to the point P. So now, after some short frequency range, we will get F2 with constructive interference, which will correspond, for example, let's say M equals 2. Okay, so it's not enough for me. I will sit, I'll keep tuning, keep changing the frequency. So now, of course, after constructive, this destructive interference will come through this point P, through the point P. So now, the next, it will be destructive interference, the second one, which corresponds to integer M equals 2. So then, okay, not enough. Let me keep tuning. So I keep changing now. This again, constructive interference will come through the point to the point P. So now it will be F3C, which corresponds to integer M equals 3. Okay, so you see what I'm getting. The first frequency, which gives me constructive interference at that point, it's a first frequency, right? Which is going to give me constructive interference at that point. Then, basically like a lowest frequency. Then, frequency which is slightly higher, which is going to give me constructive interference at that point. And then, this is the third frequency, which is going to give me constructive interference at the same point P. So that's what problem asks, actually in part B. Find 3 lowest frequencies which are going to give us constructive interference at point P. That's what we need to find. But of course, between them, there are destructive interference. Let me add another destructive interference. So let's say F3D, which corresponds to integer number 3. And so now I have first lowest frequency, which is going to give me destructive interference at point P. This is the second frequency, slightly higher, which is going to give me destructive interference at point P. And now this is the third frequency, so which is going to give me destructive interference. So I have 1, 2, 3, 3 lowest frequencies, which are going to give me destructive interference. Probably I should have started with M equals 0, but it's not a big deal, right? So we will get that naturally. First, I want to explain situation, physics, sort of the dynamics, right? So that you will realize what is the question. Because once I give it on the exam, and I think 100% of students, they just use check, right, or check, whatever you pronounced, right, without understanding what they do, what they did. Okay, so that's the explanations, and now let's get through the math. Everything should come. For now, it might sound complicated, but it's not. Now, all these we should be able to get from this condition. Everything should come from these conditions. Okay, now let's get, after sort of, I hope, understanding this, now let's get to the problem. Okay, so now let me separate these explanations. So now I feel like don't have enough space. Okay, I can use that part. Okay, back to the problem. Back to the solution, to the actual solution, because that was my explanation of the situation. Okay, so I need to rewrite conditions, because again, as I told you, everything is over there. All right, so 2 pi over lambda times delta r plus the inherent phase difference equals to m times 2 pi and m plus 1 over 2 times 2 pi. Okay, so first, inherent phase difference, probably I should frame it in red, because that's the largest amount of mistakes, or number of mistakes at that point, right? Okay, so delta phi naught is 0, so let's dump it, right? And as a result, if this is 0, what can be done with 2 pi's? can be cancelled because this term is missing, so we'll have 2 pi here, 2 pi there, 2 pi there. So as a second step, we can cancel 2 pi. Okay, agree? Because I don't want to rewrite it first without delta phi naught, and then only then I will cancel. Just trying to save space. I think it's obvious, right? So now we can dump 2 pi's as a result, right? Of course, if delta phi naught were not 0, of course, I wouldn't be able to cancel those 2 pi's. Okay, so now as a result, let me rewrite this. So it will be delta r over lambda equals, okay, let me still 2 conditions, equals to m, just m and m plus 1 over 2. Okay, now let me move lambda to that side. So it will be delta r equals to, okay, again, 2 conditions. First, m lambda for constructive interference and m plus 1 over 2 lambda for destructive interference. So that's what we get if we apply that the inherent phase difference is 0. Now, look, delta r, we can find it. Not a big deal, right? So I already discussed that quickly, but of course we will get it. So delta r can be found. Then what we need to find? We need to find frequencies, 3 lowest frequencies for destructive and constructive interference. So we need to introduce in our condition frequency. That can be easily done. We have wavelengths. Through the speed, we should be able to introduce frequency. And we know the speed of these waves. So let's introduce the frequency and then see. And then we will see. Again, delta r can be easily found. We will do it at a certain point. Right, so now let me introduce into this. So lambda equals v over f, because we need to find f eventually. Okay, so now let me rewrite these conditions with that. Okay, yeah, let me rewrite it. So it will be delta r, okay, again, 2 conditions. So it will be first m v divided by f, so that's for constructive interference, and m plus 1 over 2 v divided by f, that's for destructive interference. So that's what are we getting, right? Now, you know what, now at this point, probably, yeah, basically we need to solve for f. Now I'm thinking, should I discuss calculations of delta r? It's not a big deal. I can calculate delta r now or then. Or maybe first let me solve it for f. Let me solve it for f. No, delta r. Okay, let's finish delta r and then we'll get back to this, right? So now let's get delta r. Delta r equals to, okay, so let me separate this. So we will continue from here, but we will need to find delta r sooner or later. Right, so let me just digress for a few minutes and get delta r. Delta r, it's r2 minus r1. And then we'll get back to our conditions, r2 minus r1. All right, r1 we see, 3.75. r2 can be easily found using Pythagorean theorem. So it's a L squared plus r1 squared. Okay, I'm not going to plug numbers. You can do it. 2 meters, 3.75 meters. What are the number? 4.25. 4.25 meters. So that's R2. So plug it there. 4.25 minus 3.75, you will get 0.5 meters. All right, so 0.5, yeah. You will get 0.5 meters. Okay, so now we know delta R. All right. So, and now let's look separately at destructive interference. Let me write this lowest condition. So now actually it's a part A for destructive interference. So delta R equals to m plus 1 over 2 V over F. Okay, it looks like my neighbors are getting louder a little bit. I hope you're not hearing that. All right, look what is given and what we need to find. Delta R we just found. Given. V given. F, that's our question. And also we have M. M is an integer. Okay, so let's just solve it for F. Right, so let me move it here. So F equals, F goes up here, delta R goes in the denominator of the right hand side. So it will be M plus 1 over 2 V divided by delta R. Okay, so basically this is the final answer for part A. Now look, now we can get different frequencies depending on integer. Integer is 0, 1, 2, 3, and as a result we're getting the discrete set of frequencies at which we can have these constructive interferences, this and that, right? So you see, naturally we're getting from this condition all those. And lowest frequency, it means that we need to use the lowest integers. Lowest integers 0, 1, 2. So apply 0, 1, 2, and you will get 3 lowest frequencies. But it makes sense to add the subscript m, because now frequencies depends on your integer. It makes sense to add the subscript m naturally, right? Okay, so now, you know what, let me plug immediately numbers 340 and 0.5 in order to get sort of final expression for destructive interference case. A, destructive. So you see I grabbed only the lowest condition. Okay, so it will be M plus 1 over 2 and 340 divided by 0.5. So 0.5, it will just double the numerator, 680. So final condition, F, M. So if you want to find all frequencies at which, at this point, we're going to have destructive interference, this M plus 1 over 2 times 680, right? Let me check if I'm getting the same. Yeah, it should be. Yeah, units of hertz, of course. Maybe I can add hertz, of course. And again, let me emphasize, M equals 0, 1, 2, 3, and so on. So now 3 lowest, this. So let's apply them. So as a result, F0, M equals to 0, right? So it will be 0 plus 1 over 2 times 680. So we're getting 340 hertz at this frequency. At this point P, we're going to have the first, okay, this destructive interference. 340 hertz. So then the first, okay, the second lowest frequencies, but corresponds to M equals 1. So it will be 1 plus 1 over 2. 1 plus 1 over 2 and times 680. Okay, now I'm lazy to calculate. So it will be 3 over 2. 680 divided by 2, it will be 340 times 3. Okay, that's too much. Let me look at my notes. 1020 hertz. 1020 hertz. So that's the second lowest. And now F equals 2. I mean, M equals 2, not 3. So it will be F2 equals 2 plus 1 over 2 times 680. Okay, that's too complicated. Definitely let me look at my notes. And again, these are destructive. You know what? Let me add upper script D to all these frequencies. Upper script D. I just look at my notes, right? And I realized I should have looked earlier, right? To emphasize on that. So this is, let me add upper script D, 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 and D. So means destructive interference, frequencies for destructive. So number 1700 hertz. 1700 hertz. Okay, so that's part A. So now let's look at part B. I hope I will be able to fit it here. Right. So part B, I'm just trying to estimate the space. Okay, I hope I will be able. So part B. So now I will use, of course, this upper condition, delta R equals mv over f, right? So, you know what, let me write it here. Sorry, I'm afraid that I will not have enough space. So B, what did I say? Delta R equals mv over f, mv over f. So that's for constructive interference, right? So again, solve it for f, like we've done over here. Pretty much now we just need to repeat the same steps, but with m instead of m plus 1 over 2. So we want to know frequency, so f equals mv over delta r. And so again, it depends on integer m frequencies, so it makes sense to add the subscript m next to f. So, okay, and v over delta r, it's again 680, right? So it will be m times 680, right? Okay, so now that's the, you know what, I haven't framed this condition because basically that's the answer, right? And then we just applied. And this condition I would probably frame also, right? And in this case, the lowest frequency is 0, right? When m equals 0, but who cares about the signal with 0 frequency, right? No, we'll skip it. We'll start with m equals 1, right? So, okay, I will write f of 1 and constructive interference. Because 0 frequency, it's not a wave. It's when nothing happens. There's no wave. So that's why we're skipping m equals 0, because it doesn't make sense for us. So m equals 1. So it will be 1 times 680. So 680 hertz. That's the, at this frequency, we're going to get first constructive interference at the point P. And you see, it's between these frequencies, between this first one and the second one, because you remember, all the time they alternate. Constructive, destructive, every time. So this frequency is between these two dark. Then F2, constructive, of course it will be 2 times 680. So it will be 1360. Right? 12, yes, 1360, right? Yeah. And the last one. All right, F3 constructive. It will be 3 times 680. Okay, now it's better to look at my notes. 2040. 2040 hertz. So 3 lowest frequencies. So now I'm talking basically about this, and that, right? At which, at the same point P, we're going to have now constructive interference. So that's the problem. Again, it's everything comes from this condition. You just need to get F out of that and those integers are going to give you all these frequencies. Of course, I just spent plenty of time just trying to explain the situation, but otherwise this problem should be solved like within 10-15 minutes, right? Because it's nothing but that. So first, from the problem, statement of the problem, delta phi naught. Delta r, piece of cake. And then you just introduce f through the speed of wave. Solve it for f and plug different m's, m0, m1, m2, m1, m2, m3, and get 6 frequencies. So it's not. I wouldn't qualify that as a ridiculously complicated problem, but understanding is important. Okay, so that's the problem which I was planning to discuss in the recitation class, and in my recitation classes I only managed to get through explanations, right, without getting through these gory details. Okay, what about time? 7:15, so we've been here, okay, 3 hours 15 minutes. Yeah. So probably the last problem about double slit. And the problem which I decided to solve, it's from the lecture. You remember I solved one problem, right? And the second one I told you guys it will be in my slides. But let's just solve it, right? Which, yeah, I showed in the slides, but it's better to discuss it. Right. And again, double slit experiment, again, it was kind of a lengthy derivation, although each of those steps shouldn't confuse you. All those steps are of your level, and you should be able to understand, but you need to arrange them in a proper sequence, right? And at the end, we got this condition, right, which allows us to find a position of bright spots relative to the center of the system, where m equals 0, and then m1, m2, m3. So pretty much this gives us a distance from the center of the screen to the position of the mth bright spot. All right. And so pretty much when you need to solve the problem like this, it's nothing but about this formula. It's like in the interference, everything is in here. You just need to, I don't know, turn it inside out, solve it in terms of frequency, or maybe in terms of something else, right? Same here. It's all in this formula, nothing else. Right. Okay, so now let me discuss this problem. It's actually from the book, chapter 33 and problem 35. Again, my solutions are in slides, and of course it will be attached to this notes of this exam review session. Okay, so what we have? Double slit experiment, basically. Right. So let me write immediately. So it's a double slit setup. Right. And you know what? Let me give you a sort of physical situation when this problem is possible. Let's say you work in optical lab, right? Or maybe company, right? And let's say your boss told you, okay, go and fabricate for me, for whatever project, for whatever experiment, a double slit. All right. And he told you, okay, let's say the distance between slits must be, I don't know, let's say 0.4 millimeters or 0.5 millimeters. So boss gave you assignment, okay, scratch two slits, two holes, right, with the distance between them 0.4 millimeters. So let's say you go to the clean room, right, and somehow using whatever equipment you have, let's say you fabricate it, and then what can you do in order to check, to make sure that what you produce is what your boss wants to see? Of course, in this case, probably you can look through the microscope, right, and you can see the distance, right? But let's assume you don't have a microscope, right? So what can be done in this case? You can set up an optical table, simple optical table. You will take your fabricated double slit, take a laser, I know, something like helium neon laser, which is pretty much in every corner of any optical lab, right? and illuminate it. Put the screen at a distance which you can easily measure, right? And see this interference pattern, and see these bright and dark spots, right? Then, of course, you can use this formula, all right? You can pick, for example, a certain M, some bright spot, but the thing is, you know what? Since I show demonstrations almost every semester, except since we become virtual, right? And usually you can see on the wall that these bright spots are so jammed together. It's so even difficult which spot corresponds to m equals 0 or m equals 1. So they're close together, right? Distance between them is very small, right? It's difficult. Of course, you can measure the distance, for example, between two adjacent bright spots, but accuracy will be, okay, I don't want to use bad. Accuracy will be reasonably bad. So how can you increase accuracy in that case of your measurements? Instead of measuring, for example, the distance between two adjacent spots, you can measure the distance between all visible bright spots. And let's say you manage to count 12 bright spots over here, let's say 12 bright spots, and you measured the distance between them in an attempt to increase or reduce error of your experiment. And then using those numbers, you need to calculate, now using math, to calculate the distance between slits. Typical situation, and that's what this problem is all about. Since I work in optical labs, students fabricated all the time some devices, right? And then they go to the optical table and set up something like this in order to measure what they actually fabricated, right? So typical situation. Okay, so now let me give you what is given, and let's get through the solution. Okay, so Heaney laser. I remember first I started working in the lab and I heard this expression, Heaney. I was confused. I knew about lasers, but I never heard about this term. And then after a few days, I realized it's just a helium neon laser. Of course, I knew helium neon laser. I just didn't know about this abbreviation, Heaney laser. Right. So now whenever I say it, it reminds me about that. Okay, so double slit setup. And so we have helium neon laser, and the wavelengths, usually it's given on the laser. Let's say we know 600 wavelengths is 633 nanometers. It's sort of a reddish light, of course, give us reddish light. Then you set up your experiment and you position the screen on which you're going to see bright spots, and it is 3 meters behind the slit, or between the slit. So this distance L is L capital 3 meters. Okay, let me draw the picture and then I will continue giving you numbers. So this is our double slit, and it is illuminated by this helium neon laser. So lambda. Right. And then here is your screen on which you observe your bright spots. Okay, let me make it longer a little bit. So this is the center. And you remember y-axis, the origin is at that point, at this point. So this is y, right? And this is the origin. Then okay, let me show that this is L. It's at this L, right? And as I told you, we need to find this distance d eventually. Distance between, okay, it doesn't look good. Let me redraw it. So d, that's what needs to be found. You fabricated it, and now you just want to convince yourself that what you fabricated is what you wanted, or your boss wanted. And then, as I told you, in order to increase efficiency, you measured the distance between 12 bright spots. So let me start from the center. Let's say this is the first one. At the center of the screen, there must be a bright spot all the time, corresponding to integer m equals 0. Right, so whenever m equals 0, y is 0. So at the center, it doesn't matter which light you use, which frequency, all the time at the center of the screen, there must be a bright spot. So this is the first one. Then let's say 2, 3, 4, 5, 6. Now let me go this 7, 8, 9, 10, 11, 12. Whew, okay, good. So I managed to create 12 bright spots. And as I told you, the distance between them, again, to increase the accuracy, this is A. Let me call this distance A is 52. Oh no, centimeters is too much. Or millimeters, yeah, because I know the centimeters, it's a huge distance for a double slit. Millimeters. All right. Okay, let me write here A. 52 millimeters. Okay, and let me emphasize it's a between 12 bright spots. Whew. And we need to find D. Okay, I think that's what is given, nothing else. Yeah. That's what you can get by setting up the experiment and measuring this distance. So what needs to be found? D. Right. So the thing is, again, as I said, if you look at the double slit experiment interference pattern, it's difficult to tell which spot corresponds to m equals 0, right? So usually just you count the distance between any two bright spots, right? And then what can be done, because you have no information about m. Right? So that's the trouble. We don't know much about m. But let me ask you, in the lecture I mentioned that. What can you tell about distribution of these bright spots? After that long derivation, there was an additional slide, and I discussed that at the end of the lecture. All these bright spots are equally spaced. It means what? It means that the distance between two adjacent or consequent bright spots exactly the same. So the distance between two adjacent spots is constant, the same. So it means that let's call the distance is delta y. Let's call this delta y. So let me write these bright spots are equally spaced. Actually, I can show it quickly. Equally spaced. I can actually, let me show it. All right, let me prove it. Okay, so let's calculate delta y, which is over here, right? So what is delta y? Let me take a bright spot which corresponds to m plus 1 and subtract the adjacent bright spot which corresponds to integer m minus y sub m. Of course it will be m plus 1 times that, m plus 1 times lambda L over d minus m lambda L over d. Okay, I've done it in the lecture, but I just wanted to show that again. So this m with that factor and this m with that factor, they get cancelled. And as a result, we have term without m. It's just lambda L divided by d. So it's a lambda L divided by d. What does it mean that m is not here? It means that it doesn't depend on the integer. Delta y is exactly the same, right? So now, once you know that, how can you connect this distance between 12 bright spots and this delta y. We must connect them. There must be connection, a straightforward connection. Think for a second. But I will tell you, usually, most of the time students made a mistake here. They usually tell me this. Since n, okay, let me label that this n equals to 12, right? So they usually tell this. So A equals to n times delta y. That's usually the answer from students, but it's not completely correct. Let me show you. Let me demonstrate that it's not right. So let me write the question first. How can we connect A and delta y? Right. Okay, and now let me justify that what usually students tell me is not wrong, is not right. Look, what if we have two bright spots? Basically, n equals 2. How many gaps, how many delta y's we have in this situation? Obviously, there is only one gap between two bright spots, right? So this is delta y. So in this case, so how can we write distance between two bright spots equals to 1 delta y, right? So we have, let me write this like in my notes, n equals 2. Then we have one gap, and so as a result I can write 1 times delta y. Now let's assume that we have 1, 2, 3 bright spots. So now n equals 3. How many gaps we have? 2. So we have this delta y and that delta y and delta y. So we have n equals 3, but now we have 2 gaps, and the distance between these 3 bright spots can be written as 2 times delta y. Then what if we have, let me look at one more situation. 1, 2, 3, 4, n equals 4. Now we have 3 gaps. 1, 2, 3. So delta y, and delta y. So now we have 3 gaps. And we have 3 times delta y. That's the distance between 4 bright spots. So now we can, you see the pattern, and now we can write the relationship between the distance between n bright spots and a number of gaps. So now in general, so if we have, in general, let's say we have n bright spots, we have of course n minus 1 gaps, and then we can write the expression which we wanted to use in our problem. So it's n minus 1 times delta y equals to the distance between 12 bright spots. Usually, as I told you, students their first response is just n times delta y equals a. No. Number of gaps is smaller by 1. So it will be 11 gaps times distance between 2 adjacent spots equals to a. So that's what we needed. All right. So pretty much now what we need to, instead of delta y, we need to plug this and solve it for d. Okay, let me do it eventually. So now, n minus 1 times delta y, it's a lambda L over d, and equals to the measurement in your experiment. With the ruler, you measured the distance between 12 bright spots. Again, n is given because you measured 12. Lambda, we know the laser. L you set up the experiment, you know the distance to the screen. And D, that's what you want to get eventually, to confirm that you managed to achieve what you wanted to achieve. Right. Okay, so that's our unknown. Right. So now let's solve it for D. Or maybe let me write it underneath. So D equals, D goes up here, A goes downstairs. So it's very simple. So it will be n minus 1 and lambda times L and divided by A. Of course, millimeters must be converted to meters. So to make sure that units are correct, you can do it. I will, of course, skip it. All right, and I will just write down the answer. 0.4 millimeters, typical distance between slits. So it will be equal 0.4 millimeters. Whew. So almost 3 hours, 35 minutes. I think it should be enough, right? There are some additional problems, right, between these, so you can look at by yourself. Right? So that's, we just discussed the new material again, which we discussed after the second midterm exam.